Dear student, in today's lecture we start chapter number 8 from the syllabus of Maharashtra State Board, Electrostatics. Now what exactly mean by the electrostatic that we have to learn? Electrostatic is the study of electric charges at rest. Study of electric charges at rest is called as electrostatic. Means in this chapter, so we have to deal with the charges, stationary charges. So as well as in previous standard, we already learned some concepts such as properties of charges as well as some basic things about the charges. So charge on particle is property by virtue of which it produces electrical influence around it. And charge having a property to produce electric field in its surrounding area. Charge are of two kinds, positive charge and negative charge. You already aware with this. You already learned in the previous standard, like charges repel each other, whereas unlike charges attract each other. Like repel, unlike attract. Like means same charges, positive, positive, they repel. Negative, negative also repel. Whereas unlike charges, unlike means a different, positive charge and negative charge. They attract each other. So here we written this statement. Now in previous standard we already learned Coulomb's law. This Coulomb's law gives us idea about how much force of attraction or repulsion exists between any two electric charges. Now let me learn this Coulomb's law because this is a very important article in this chapter point of view. Now statement. So statement, in that statement, let I tell you here one thing. So if I consider two charges, Q1 and Q2, I consider two charges, Q1 and Q2. They are separated by a distance r. Then force of attraction or repulsion between these two charges directly proportional to product of charges. Directly proportional to product of charges. And this force inversely proportional to square of the distance between two charges. If we combine both the observation, then we get an equation F proportional to Q1 Q2 divided by R square. And this is the Coulomb's law of electrostatic. Now if you see the statement, so this is the electrostatic force of attraction or repulsion between two charges. We are considering point charges. Is directly proportional to product of the charges and inversely proportional to square of the distance between them. Or the same law we can write by replacing this proportionality sign by is equal to sign. Then we have to write constant. So we written here the constant K. K is the constant. And that constant is called as proportionality constant or electrostatic force constant or Coulomb's constant also. This constant having a different names. Now, how much is the constant that everyone know? How much is the value of this constant? This constant is given by this formula 1 upon 4 pi epsilon 0. Now, epsilon 0 is what? You can see here, epsilon 0 is permittivity of free space. Epsilon 0 is permittivity of free space. Now, if we substitute this constant in the formula, if we substitute this constant in a formula, then we get one more thing we remember. So in the formula, I told you here, this is permittivity of free space. Okay? Means free space or vacuum basically. The same constant we have to write for a medium. Instead of epsilon 0, we can use epsilon only. Permittivity of the medium. We can use only epsilon. You can see in the next equation. So K for a medium is 1 upon 4 pi epsilon. Now epsilon is permittivity of medium. Okay, it is the permittivity of medium. Or you can write here. Okay, epsilon is as a absolute permittivity. So epsilon is as a absolute permittivity. Now we can write one more thing you must know here, dielectric constant. Dielectric constant or relative permittivity, or you can write as a specific inductive capacity, and it is given by formula. This K is equal to epsilon upon epsilon 0. Okay, it is the formula of dielectric constant K. So dielectric constant is ratio of epsilon divided by epsilon 0. So epsilon is permittivity of medium divided by permittivity of free space, or you can write vacuum. Okay, so by using that formula we get epsilon is equal to epsilon 0 K. So this formula we get. So we can use epsilon, or you can use epsilon 0 K in a formula. Take it. Now after that, in vacuum, if we consider the vacuum, then the formula of the Coulomb's law we can write F is equal to 1 upon 4 pi epsilon 0 Q1 Q2 divided by R square. So this is the formula for electrostatic force in vacuum. In a medium, when we are considering same force, means electrostatic force between two charges in a medium, we can write this formula like this. This epsilon 0, instead of epsilon 0 K we are written. Okay? And this K is dielectric constant. K is dielectric constant. Now how much is the value of K? That also you have to remember. You remember, for vacuum or for air we are taking K as a 1. For other medium, K is greater than 1. If you consider metal, then the value of K is infinity. For metal, the K is infinity. As well as you remember here, epsilon 0 is permittivity of free space. It is having a value 8.8542 into 10 raised to minus 12 in SI system. And if you substitute this value in this formula, 1 upon 4 pi epsilon 0, you know the value of pi, then we can write its value after the calculation is 8.9875 into 10 raised to 9. Or we can round up this number and we can write the value of this epsilon 0. It is 9 into 10 raised to 9 Newton meter square per Coulomb square. So this is the value that we are taking in the problems. Okay, but if you calculate by substituting this value, you get this is the value of 1 upon 4 pi epsilon 0. Then after this, we consider here two charges Q1, Q2. You can see in a diagram, the first charge is Q1, second charge is Q2, distance is R. Then force acting on charge Q1. Okay? This is the force acting. Maybe here it's a attraction force. F12 is mentioned. Okay? Or we can write like this way. So instead of this, we can write the force acting on 1 due to 2, F12, and here F21. Okay? Similar manner, when the charges are like, then the repulsion force is there. So this is the force acting on charge 1. This is the force acting on charge 2. Okay. Now we can write the formula of F12 and F21. You can see here the vector form. You know the unit vector. In 11th standard we learn unit vector is vector divided by its magnitude. So here vector is always equal to magnitude multiplied by unit vector. Magnitude multiplied by unit vector. So this is the formula for vector. So magnitude, you know that when two charges we consider, the magnitude of the force is 1 upon 4 pi epsilon 0 if they are in vacuum. If they are in other medium, epsilon 0 k we write. Q1, Q2 divided by R square. This is the magnitude. Okay? Multiplied by unit vector. So this is the unit vector. And you remember one thing here. This unit vector must be in the direction of this force. So when we are writing this formula, so that time if this is a vector A bar, this is the unit vector which having a same direction. So this and this both having a same direction. Similar manner we can write F21. So here we are written unit vector. So unit vector having a same direction to this force, that you have to note here. Now after this, unit of charge. You know that in SI system, unit of charge is Coulomb. Because of the great contribution of scientist Coulomb in this, we are given the name of the charge as a Coulomb. So SI unit of the charge is Coulomb. Now some more basic concept, electric intensity. This is the formula of the electric intensity which we already learned in the previous standard. Electric intensity, it is F by Q0. Generally, electric intensity is the term which is used to express the strength of electric field. Which is generally used to express strength of electric field. Now for that, I tell you simple example. If I consider a charge, this is a charge Q, and this circle represent electric field area of this charge Q. And we have to find out electric intensity at point A. This is the point A, and at point A, we have to write electric intensity. Then at this point A, we have to place a test charge, unit positive charge, Q0. If you place unit positive charge, and if this is a charge, then this charge is repelled by charge Q with some force. Okay? And that force per unit positive charge is called as electric intensity. Or we can say that force acting on this unit positive charge at point A is the electric intensity at point A. Now when we consider this charge Q0 is at point B. The force is different. So electric intensity at point B is a different. So electric intensity is force acting on unit positive charge at that point is the electric intensity. So we have written the formula of electric intensity is F by Q0. F by Q0 is the formula of electric intensity. Now you know that how much is the force acting on this charge. We can write by this formula 1 upon 4 pi epsilon 0 Q Q0 divided by, if I consider the distance between these two is R, so R square, and divide by this Q0. Again, if this is a F, then F by Q0. So if we divide this equation by Q0, we get 1 upon 4 pi epsilon 0 Q by R, sorry, R square. This is the expression for electric intensity which we already derived. Okay. Now you note one thing here. Electric intensity having a unit, Newton per Coulomb. So unit of force is Newton divided by unit of charge is Coulomb. So Newton per Coulomb is the unit. Now how we get this volt per meter? So one more formula of the electric intensity that we have to learn in the next article, it is dV by dx. So unit for V, volt, unit for distance, meter, volt per meter is the electric intensity. Now some formulas you can see here. When these are the two charges, this is the force that we already discussed. Electric intensity is this. Okay. Then electric intensity is given by F by Q0. This Q0 get cancelled and we get this formula for electric intensity. We can write only Q. Okay. We can write epsilon or epsilon 0K here. This is the expression for electric intensity. And you remember, electric intensity is a vector quantity. You can see the direction here. So direction of the electric intensity is away from positive charge. After this electric intensity, next article is electric lines of force, which you already learned that we have to revise here. What is electric lines of force? They are the imaginary lines drawn, okay, to pictorially represent the electric field due to the charge. Now these are the electric lines of force. You can see a diagram. This is a positive charge and negative charge. This is positive and this is negative charge. And these are the electric lines of force for positive and negative charge. Now if you see this diagram very carefully, now you come to know about some properties of the lines of force. They start at positive, they end at negative. You can see here direction. Start at positive, end at negative. Okay, never intersect, pass through insulator but does not pass through conductor. Okay, and they always start and end perpendicular to the surface. Here initially they start perpendicular to the surface and then they form a curve here. Start, end, normal to the surface. This is the property of electric lines of force. Now electric lines of force crowded, where electric intensity is large. You remember, electric intensity large means what? They are crowded near charge. Near charge, electric intensity is more, so they are crowded near charge. Okay. Now after that, area vector. So this area vector is very important. because in many derivations we have to consider area vector. Generally, area vector represented by ds. We represent this area vector by ds bar. Now let I show area vector in a diagram. So I consider this is the area S. This is area. Now in that smaller area I consider ds. ds is the smaller area. Now area vector is represented in this diagram. So this is the area vector. You can see here ds bar. This is the area vector. Area vector is perpendicular to the surface of area. You remember one thing here. You note one thing. Area vector is perpendicular to the surface area. Okay. So area vector we can write like this. Area multiplied by unit vector. You know that any vector is equal to magnitude multiplied by unit vector. Now after that, next term is electric flux. Now what is electric flux that we have to remember? So this is the basic which we already covered that we are revising here. So electric flux is total number of electric lines of force. Just we covered electric lines of force. So total number of electric lines of force that normally pass through that surface. Total number of electric lines of force that normally pass through that surface is called as electric flux. So electric flux is what? Number of lines of force, okay, which are passing normal to the surface. Generally, electric flux we write by symbol phi. We represent symbol phi for electric flux. Now I consider this is a surface area S. This is the electric intensity E. Now I consider this is area. This is area element or area vector ds bar, which is having a same direction as the direction of electric intensity. Now if I consider one more area vector which making some angle theta with direction of electric intensity. So you can see here. So this electric intensity direction and this is area vector. Okay. Then if I consider one more area vector which is making angle 90 degree with the direction of electric intensity. Then electric flux through small area element ds. Electric flux through small area element ds due to this electric intensity at an angle theta is, it is given by this formula E bar dot ds bar. Now here EDS into cos theta. You know that A bar dot B bar is equal to AB cos theta. This is the dot product, scalar product. Now here EDS cos theta. Now pay attention here. When you are considering this angle, okay, this is the angle. Now pay attention. Theta is what? Angle between E and this ds or area vector. Now pay attention here. If the angle is, here angle is 0, so we can write flux is E into ds. Now here angle is theta. So here angle is theta. So we can write electric flux is equal to E into ds into cos of theta. Okay? So here angle is 90. E into ds into cos 90 is 0. So electric flux is 0 here for this case. Hence we consider three cases here. Okay? and we consider this is case 1, this is case 2, and this is case 3. And in every case, we are written electric flux. Okay, as well as if you want to write for a closed surface, electric flux over the whole surface S, then we can take integration. We can take integration, and this circle on this integration sign indicate that integration over a closed path, E bar dot ds bar. So that we can write like this. Okay? You remember here, electric flux is a scalar quantity. Okay? Electric flux is a scalar quantity, but because it is the scalar product of E and ds. SI unit of electric flux is Newton meter square or voltmeter. Unit of E multiply electric intensity multiplied by unit of area. Okay? Newton meters first unit. You know that E into ds. Unit of electric intensity is Newton divided by Coulomb, and ds is meter square. So you can see here the unit Newton meter square per Coulomb. As well as I told you one more unit for E, volt per meter, and unit area is meter square. So meter get cancelled. Volt meter is the unit. You can see 2 units for electric flux. I hope you understood this area vector. Now next one is continuous charge distribution. Now what is continuous charge distribution? When charge is uniformly distributed over the length, over the surface, over the volume, it is considered as continuous charge distribution. Now in that, we have to consider 3 points. Linear charge density. Linear charge density. It is generally represented by lambda. Now what is linear charge density? Now let I tell you formula here. Okay? Linear charge density is charge per unit length. When we consider straight conductor, charge is uniformly distributed over that. Charge per unit length is linear charge density. So we consider here a one straight conductor. So this is straight conductor. Okay? And charge is distributed on that. So this is the smaller element, smaller area, smaller length. On that charge is distributed, and that charge is dq, and the length is ds. Then linear charge density is given by formula q by l. So this is the linear charge density. Unit is charge unit divided by length unit, Coulomb per meter. Coulomb per meter is the unit. Or we can write dq by dl for this smaller portion. Next one is surface charge density. Surface charge density is charge per unit area. Charge per unit area is the surface charge density. Unit is Coulomb per meter square. Let I consider this is the area. On that area ds, so this is the area ds. Charge is dq. Okay, so we can write surface charge density is charge by area s, or we can write dq by ds is the surface charge density. Unit of charge divided by unit of area is the unit of surface charge density. Now volume charge density, it is generally represented by rho. Charge per unit volume. Charge per unit volume is called as volume charge density. Unit is Coulomb per meter cube. Now I consider a cubical surface on that a charge is uniformly distributed. Now I consider smaller part of that having a volume dV and charge is dq. Then we can write a volume charge density q by v, or for this smaller part we can write dq by dv is the volume charge density. So I hope you understood this continuous charge distribution. After this continuous charge distribution article, next one we have to learn Gauss theorem. Gauss theorem we already covered in the previous standard. See this Gauss theorem. So this statement represent the Gauss theorem. So phi electric flux, E for electric flux. Generally phi we can use for the magnetic flux also. E for electric. Electric flux is equal to Q upon epsilon 0. Q is the total charge, epsilon 0 you know that, permittivity of free space. So what is the Gauss theorem? So Gauss theorem is electric flux is equal to phi is the electric flux coming out of the closed surface. Electric flux is equal to total charge divided by this permittivity. Q is the total charge, okay, over the closed surface. So this is Gauss theorem. So if I consider a charge inside this surface is Q at point O, then this is the formula of electric flux, and it is equal to total charge divided by epsilon 0. I hope you understood Gauss theorem. Gauss theorem. Now pay attention. So in mathematically, we can write Gauss theorem by using this formula. So this is the mathematical formula of Gauss theorem. So in that formula, this symbol phi E is total flux coming out of closed surface. Q is total charge inside the closed surface. Pay attention, Q is total charge inside the closed surface. Then the Gauss theorem gives total flux coming out of the closed surface, which is equal to total charge divided by epsilon 0. Epsilon 0 is permittivity of free space, and which is equal to integration of E bar dot ds bar. This circle on the integration sign indicate that integration over a closed path. Okay, E bar dot ds bar. So this is the Gauss theorem. So statement of the Gauss theorem in word is displayed here. I hope you understood what is Gauss theorem. Now after this we have to learn applications of Gauss theorem. We have to use Gauss theorem, and by using Gauss theorem we have to calculate electric intensity near charged body. Now let's see the first application. So before the first application, one problem from the exercise we have to learn. See this problem. So it's a problem number 7. It's a question number 7. Okay? From page number 213. Now pay attention. What they given in this question? Two charges. Pay attention. Two charges. The first charge is minus Q. Second charge is plus 2Q. First charge minus 4Q and second charge is plus 2Q. Located at point. So this is the location of the minus Q charge, and second charge location is phi A comma 0 respectively. What is electric flux? What is electric flux due to these charges through a sphere of radius 4a? with its center at origin. Now, pay attention, just we learn electric flux is equal to total charge divided by epsilon 0. So this is the formula for the electric flux. Total electric flux over a closed path is equal to total charge enclosed by that surface divided by epsilon 0. This is the formula. Now let me use this formula. So before writing any answer, let me draw a diagram for given question. So this is the diagram. Now pay attention here. Two charges. I shown both the charges in a diagram. First charge minus 4q. You can see here this charge minus 4q. Whose location is, so this is the location 2a comma 0. You can see here. So it is 2a comma 0. This is the coordinates of this charge. Coordinates of charge minus q. Okay. Now second charge is plus 2q, which is located at phi a comma 0. So the second charge I shown here, and this is the coordinates of this charge. Okay. What is electric flux? We have to find out electric flux due to these charges through a sphere of radius 4a. Now pay attention here. This is very important. Now I consider a sphere. I consider sphere of radius 4a. Okay, means here it's a 4a. So if the radius is 4a, it means that one charge is coming inside the sphere whose radius is 4a. This minus q 4q is inside the sphere, and this plus 2q, this charge plus 2q is coming outside the sphere because the coordinates are phi a comma 0, means it is at distance phi a, okay, which is outside the sphere. Now by Gauss theorem, what is the Gauss theorem? Electric flux, by Gauss theorem, electric flux is total charge enclosed divided by epsilon 0. And how much is the charge enclosed by this surface? Is only this minus 4q. We are not considering outside charges. So here, according to Gauss theorem, electric flux phi e is q by epsilon. I written here q enclosed, charge enclosed by that surface, which is minus 4a, minus 4q, divided by epsilon 0. So this is the electric flux. Here you note one thing here. You note one thing. This charge plus 2q will not contribute to the flux as it lies outside the Gaussian surface or outside the sphere whose radius is 4a. So this is the answer for the question. I hope you understood how we get this answer. Now, after this, we have to learn a next article, and it's applications of Gauss theorem. The first application we have to start. First application is electric field intensity due to uniformly charged spherical shell. We have to consider a spherical shell having some charge which is uniformly distributed over its surface. And we have to consider, in that we have to consider the first point. We have to find out electric intensity, electric field intensity due to charged sphere for a point which is outside the shell. For a point which is outside that spherical shell. Now I consider here a spherical shell. You can see in a diagram. This is a spherical shell. Some charge is uniformly distributed over the surface of this spherical shell or over the surface of sphere. You can see positive charges here. O is the center. Capital R is the radius. Capital R is the radius, and this is a hollow spherical shell that you remember. Okay? And radius is capital R. Now we have to consider a point P. Point P, which is outside the shell. Okay? We have to consider one point which is outside the shell. So this is the point P. You can see a point P in a diagram, which is outside this spherical shell. Now, to find out, pay attention, to find out electric field at point P, to find out electric intensity at this point P, we consider a Gaussian surface. We consider a Gaussian surface. Okay, we consider Gaussian surface. You can see Gaussian surface by dotted line in a diagram. Now, what is the Gaussian surface? Okay, Gaussian surface means the surface, on every point of the surface, electric intensity is same. Electric intensity is same. Now, you can see this point P. The same electric intensity you can find out at this point. You can see here, I shown red dot. One more point I can show here. On this point also, electric intensity is same as the electric intensity at point P. So here we consider one more point, electric intensity is same. So Gaussian surface means the surface at every point of the surface, electric intensity is same. Okay, that surface is the Gaussian surface. Now we consider Gaussian surface. Okay, if I consider R is, this R is a distance of this point P, then we drawn here Gaussian surface whose radius is R. It's a Gaussian spherical surface whose radius is R, small r. Now, we consider a small area. We consider small area. Okay. ds is the area. This area you can see, this is the ds. By the pink shaded area is the ds. Now at this area, we can draw area vector. So this is the area vector ds bar. In yesterday's lecture, in the last session, we already learned what is the area vector, what is the direction, everything we learned. So this ds bar is the area vector. As well as at point P, at this point P, what is the direction of electric intensity, that also we have to discuss. Now see, in the diagram you can see direction of electric intensity. So this is direction of electric intensity. And this area vector, it is also along the same line. So area vector and electric intensity directed along the same line means they're having a same direction. Now we can use Gauss theorem. So by Gauss law, electric flux is equal to integration of E bar dot ds bar is equal to Q by epsilon 0. So we already have this formula by Gauss law. Now we have to use this formula and we have to solve this equation for electric field intensity. Electric field intensity. You remember one thing here. So in previous standard you learn A bar dot B bar is A B cos theta. That you remember. This formula we have to use. So here E bar dot ds bar. We can write E ds cos theta. Let I write in next step. So this electric flux as it is equal to integration over a closed surface. So this integration means that over a closed surface is equal to E ds cos theta is equal to Q by epsilon 0, because Q is the total charge here. This Q is the charge. Okay? So this Q, you can see Q in a diagram also. But here E bar and ds bar, they are in the same direction that we already discussed. So angle theta is 0. Then how much is the cos 0? Cos 0 degree is 1. Cos 0 degree is 1. Let me substitute this value in above equation. So what we get? So we get this formula. You can see here the formula. So this E bar I taken outside. The reason is electric intensity is constant over the Gaussian surface. So E is constant, taken out. Integration ds, and this cos theta is what? 1. So that also we substituted. Q by epsilon 0. So this is the next step. Now in this formula we have to substitute here integration of ds. Integration of ds we have to substitute. Now this ds, you can see in a diagram. So ds is this smaller area element. Integration of ds gives the total area. Integration of ds is the total area. Total area of what? Total area of this Gaussian surface that you remember. Because this ds is on Gaussian surface. So integration ds is the total area. Now you know that this Gaussian surface is spherical. So area of sphere is 4 pi r square. This is the surface area of the sphere. You can see radius is r. So 4 pi into small r square. Now let I substitute here. This E as it is. You can see here E as it is. Then integration. This integration of ds, we are written 4 pi r square. Because area of the Gaussian surface is 4 pi r square. And this Q by epsilon 0 as it is. So we get equation E into 4 pi r square is equal to Q by epsilon 0. Now this equation we have to write for E. Capital E is equal to. We transfer this 4 pi r square towards right hand side. Now let's see what we get. Now we get the formula of electric intensity, which is Q upon 4 pi epsilon 0 r square. And this is a final expression for electric intensity. Final expression for electric intensity due to uniformly charged spherical shell and at point outside the shell. At point outside the shell. Now here in this formula we can substitute here. Q is equal to, you know the one formula here. So sigma, last time we learned sigma is surface charge density. Surface charge density. Surface charge density means charge upon area. So sigma is Q by ds. So by using that we can write Q is equal to sigma into ds. So this is the formula. But ds, so here when we are writing for total surface, this ds is the area, and area of this charge sphere. So sigma, here area of the charge sphere is 4 pi r square. When we are talking about this charge sphere, radius is capital R, you can see here. Okay, sigma is surface charge density of this charge sphere. So this ds we have to consider area of this charge sphere. So it is 4 pi r square. So we get Q is equal to sigma into 4 pi r square. That we substitute in this equation. Then what we get? So after substitution, you can see here E is equal to, instead of Q, sigma 4 pi r square divided by 4 pi epsilon 0 small r square. Now 4 pi get cancelled. You get this formula. Sigma r square divided by epsilon 0 into small r square. And this is the electric intensity formula. So both the formulas, and this formula as well as this formula, both are the formula of electric intensity. When the problem is asked on this article, you can use this both the formulas as per your convenience. Now after that, you remember here one thing. The electric field due to uniformly charged thin spherical shell at a point outside the shell is such as if the whole charge were concentrated at the center of shell. Now pay attention. So when we are considering this spherical shell, we consider here the whole charge is concentrated at the center of the shell. Okay, then we can consider the electric field due to the uniformly charged spherical shell. Now here we finish the first application. I hope you understood. This is very easy mathematical steps. Now after this first application, so in that we can write two more cases. Now which two cases we can learn here? Pay attention, here I consider the point P outside. So pay attention here, the point P we consider outside. Now we can consider point P on the surface as well as inside the surface. Two more cases of the same formula. You remember this formula for that. So case one, if a point P on the surface of shell, if the point P on the surface of shell, you can see here a same sphere, radius r, and the point P. You can see here the point P, which is shown on the surface. You can see here, this is the point which is shown on the surface of spherical shell. Now I consider this area element, small area element ds. This is the area vector ds bar. Electric intensity is again in the same direction shown in a diagram. Now by Gauss law or by first application, we can write by first application, Gauss theorem first application. So this is the formula which we already derived. In that formula, you can remember here. So distance of point P is small r. Small r is what? Distance of P in the previous derivation. Okay? Capital R is what? Radius of charged sphere. Now when we are talking about this case, in that case, so here this is capital R and small r, both are same. Both are same here. So we can write here small r is equal to capital R. Let me substitute in above formula. So what we get? If small r and capital R is same, then this r get cancelled. So we get sigma by epsilon 0. We get sigma by epsilon 0. And this is electric intensity on the surface of spherical shell. This is electric intensity on the surface of spherical shell. So we finish this case. Now the case number 2. Case number 2. If the point P, in the case number 2, we have to discuss if the point P inside the shell. If the point P is inside the shell. Again, same diagram we are considering. Again, we are considering same diagram. Hollow sphere, capital R is the radius. Now point P, you can see point P in a diagram, which is inside the charge sphere or charge shell. Now in that case, so dotted sphere is shown. Now this is the radius is R dash for that dotted sphere. We consider area element. Okay? Area vector ds bar is shown in a diagram. Electric intensity is also shown, both having same direction. Now we have this formula by Gauss theorem first application. Now here, when we consider the charges, charges are on the surface. So inside the shell, you note one thing here, sigma is 0. Sigma is what? Surface charge density, charge per unit area. So it is 0 for inside the point. If it is 0, then if we substitute sigma is 0, we get E is equal to 0. We get E is equal to 0. I hope you understood this. Now you can remember one thing here. So here, this property E is equal to 0 inside the cavity. Means when we are considering the cavity, cavity means a space inside the charge body. That is the cavity here. So electric intensity is 0. And it is used for electrostatic shielding. So simple example. So in your textbook, one question they ask. So this is the question. The safest way to protect yourself from lightning is to be inside a car. Justified. Pay attention in rainy season when the lightning is happening. When the lightning is happening, the safest place is inside the car. Because for inside point, we already learn electric intensity is 0. Electric intensity is 0 for inside point. So this is the explanation of this question. See this problem. So this is the problem based on a Gauss theorem application number, a Gauss law application number 1. Now let us explain. A spherical shell of radius 10 centimeter. You note down this radius. Radius is 10 centimeter. Carrying a charge. Charge is 1 microcoulomb. Is placed in air. So it is placed in air. This is also very important. Calculate the magnitude of electric field intensity at a point at a distance 30 centimeter, 10 centimeter and 5 centimeter. So this is the question. Now pay attention. So this is a spherical shell or sphere. Radius is 10 centimeter. Okay? 10 centimeter is the radius. Now I consider some points. So we consider some points. The first point, which is at 30 centimeter, I consider this is a point. So we consider this is the first point. Okay? Let I write A. Okay? 30 centimeter. Second point is at 10 centimeter, means here. So this is second point, which is at 10 centimeter. And third point, which is at 5 centimeter, means here, which is asked in the point C. So this distance is 5 centimeter. Distance of this B is 10 centimeter and distance of this is 30 centimeter. And we have to find out electric intensity. We can use the formula E is equal to 1 upon 4 pi epsilon 0 Q by R square. This formula we can use. See the answer. I displayed the answer. Charge is 1 microcoulomb. that we can convert into the Coulomb. Micro means 10 raised to minus 6. Okay? The first point, R is 30 centimeter. For this point, R is 30 centimeter. So, in a formula, 1 upon, we can write like this well. So, 1 upon 4 pi epsilon 0 q by R square. And this 1 upon 4 pi epsilon 0, 1 upon 4 pi epsilon 0 having a value 9 into 10 raised to 9 in SI system. Okay, so we substitute this value here. Q is 1 into 10 raised to minus 6 and R 0.3. Why we convert into the meter? Because we substituted this 1 upon 4 pi epsilon 0 in SI system. So this is 0.3 is the distance, 0.3 square. After solving this, we get the answer. And answer is 10 raised to 5 Newton per Coulomb. So this is the answer. So 10 raised to 5. So first is over. Now second, when the distance is 10 centimeter, you know the radius is 10 centimeter. Means on the surface, again same formula we can use. Same logic, only here distance 0.1, we get 9 into 10 raised to 5 Newton per Coulomb electric intensity. But when we are coming to the point which is inside, so R is 5. So we are not using formula. We are not using formula. We are directly using here Q is equal to 0. So Q is 0 means obviously electric intensity 0. Or you can write the point is inside the sphere, and if it is inside the sphere, electric intensity is 0. So E is 0. Jar tumhi kai kelo, if you use this formula and if you try to obtain the answer, you get some answer. But you note one thing here, electric intensity for inside point is 0. So E is coming 0. So this is the answer for this question. Second application we have to start. Second application of the Gauss theorem is electric field intensity due to an infinitely long straight charged wire. So we have to learn electric intensity due to infinitely long straight charged wire. So we consider this is a wire, and through this wire some current is passed. Okay, some charges are passed. The length of this wire is, it's a infinity. It's an infinitely long wire. So length is infinity. You can see here the length. Here minus infinity to plus infinity. We already written here infinitely long straight charge wire. Now to find out electric intensity near this wire, we consider a Gaussian surface. We consider Gaussian surface. And that Gaussian surface is in the form of cylinder. You can see a green color cylinder. So this is the Gaussian surface. Yesterday I told you Gaussian surface means the surface at every point of the surface electric intensity is same. It is constant. That surface is the Gaussian surface. Now, so here we consider the length of this wire is L. Lambda is charge per unit length. It is called as linear charge density. So this lambda is called as linear charge density. So charge upon length. Now this Gaussian surface is a closed surface around a charge distribution such that electric field intensity has a single fixed value at every point on the surface. Since electric intensity is same on the surface. I consider, let R be the radius of this Gaussian cylinder. You can see this R is the radius. And we have to consider the point which is at a distance r. The point we have to consider, and that point is at a distance r from the long straight charge wire. So length of the Gaussian cylinder is L. We consider, so this is a area. You can see here a blue color area A. Then after that, area vector ds bar at this surface A. Electric intensity is directed perpendicular to this area vector. So you can see the direction of this ds area vector and this electric intensity. Now I consider another part of this Gaussian cylinder, this surface B. It's a B, you can see a surface B in a diagram. Now at B, the direction of area vector is this, and electric intensity. This is the electric intensity. Again, you can see here electric intensity and area, both are perpendicular. Now I consider one more area, small area, and it is represented by C. So at C, area vector is ds, and electric intensity is also directed in the same direction. This is the area vector ds and this is the electric intensity. You can see the direction is same. So here we consider three cases. This is 1A, this is B, and this is C. At the 3 point we discuss the area vector and direction of electric intensity. Now from Gauss law, we already know Gauss law. So electric flux is equal to integration of E bar dot ds bar. E bar dot ds bar is equal to total charge enclosed divided by epsilon 0. This is the formula. Now same Gauss law, this term E bar, integration of E bar dot ds bar over a closed surface. So over a Gaussian surface we are considering. So we have to consider this part. So this is the A part first, then B part and the C part. All the three parts we have to consider. So you can see here. So this integration over a closed surface is addition of this integration E bar dot ds for this part A, for the part B, for the part C. You can see here three part. So we have taken integration at 3 points. Okay. Now everybody know that this A bar dot B bar is AB cos theta. Similar manner, E bar dot ds bar is E ds cos theta, and theta, you know that at A what is theta, at B what is theta, and at C also. Okay. So everywhere how much is the angle, that you can find out by the diagram. Now let me substitute that. So you can see the next step. Again, the left hand side as it is, integration over a closed surface E bar dot ds bar is equal to integration E ds cos 90. You can see here this at part A, the angle is 90 degree here. Okay. So at B also angle is 90 degree. So again same we are getting integration E ds cos 90. Similar manner at point C also, but at point C both having a same direction, the area vector and electric intensity. So angle is 0. So here E ds cos 0. Now you know that cos 90 is 0. So it is coming 0. So 0 multiplied by E ds coming 0. This is also cos 90 0. So these first two terms get cancelled and we get only this E integration of ds, because cos 0 is 1. You know this cos 0, this value is 1. So we get the next term E integration of ds. In that formula only we have to substitute this integration of ds. We have to substitute integration of ds. ds is what? Smaller area element. Integration of ds is the total area of Gaussian surface. Total area of Gaussian surface. And you can see here the Gaussian surface is cylindrical in shape. It is cylindrical in shape. So we have to write surface area of cylinder. We have to write integration of ds means surface area of cylinder. Okay? You can see in the next step. Okay? So here we are written. This area is 2 pi r multiplied by L. So 2 pi r multiplied by L is the integration of E bar dot ds. So integration over a closed path E bar dot ds is E multiplied by this area of cylinder, Gaussian cylinder is 2 pi r into L. Surface area, that you remember. We are considering surface area of this Gaussian cylinder. Now we get this term. This term we can substitute here. In this E into 2 pi r L we can substitute here, and is equal to Q upon epsilon. But Q we can write by this formula. You can write Q is equal to lambda into L. So you know that lambda is what? Charge per unit length. So Q is lambda into L. So we substitute instead of Q lambda L. Lambda is a linear charge density, means charge per unit length. Now we can see in the next step, instead of this Q by epsilon 0, we write that. You can see here Q by epsilon 0. I told you lambda is Q by L. Okay? So Q is lambda L. So you can see here instead of Q I written lambda L. So instead of this I written lambda L. So I can consider this is equation 2. And the equation 1 is this equation. This is equation 1. Okay? So this is equation 1, and by this we get equation 2. So both the equation gives us this. So we can equate this. So next step we get this E into 2 pi RL is equal to this lambda L divided by epsilon 0. Now you know that integration over a closed path E bar dot ds bar is equal to Q by epsilon 0. This is coming E into 2 pi RL, and this Q by epsilon 0 is lambda L by epsilon 0. Now we can cancel the common term. Now here L get cancelled. L get cancelled. And we have to write formula for electric intensity. So E is equal to, you can see formula. E is equal to 1 upon 2 pi epsilon 0. And this 2 pi and R we are shifted to that side. Okay? So it is divided to this side. So we rearrange the term and we are written 1 upon 2 pi epsilon 0 lambda by R. Okay? We are written formula for this E. Then we get this. Now the same formula we can write in a different manner also. Multiplying by 2 and dividing by 2. You can multiply by 2 and divide by 2. So why I multiplied and divide by 2? Because when the question is asked in problem, you know the value of this. 1 upon 4 pi epsilon 0 is 9 into 10 raised to 9 in SI system. So that's why we arrange this term 1 upon 4 pi epsilon 0. So when the question is asked in the problem, no need to calculate this part. Okay? So otherwise the calculation is little lengthy. So if you multiplied by 2, divide by 2, this term 1 upon 4 pi epsilon 0 is adjusted, and that term you know that it is 9 into 10 raised to 9. So we get the formula of electric intensity. This is the electric intensity. Now in vector form, we can write the vector form. So you know that vector form, how we write vector form? Any vector is a magnitude multiplied by unit vector. So magnitude, this is the magnitude. Okay, this is the magnitude. multiplied by unit vector only. So this is the unit vector. You can see r cap is the unit vector. That's it only. Now, the direction of electric field intensity is radially outward. You already seen here. The electric intensity is away from that wire. It is radially outward from the positive line charge. For negative line charge, it will be radially inward. Instead of that, if we consider a negative charges, so it is towards that wire. Okay. As well as you note one thing here, electric field intensity is independent of size of Gaussian surface. Size of Gaussian surface. Electric intensity does not depend on the size. You can see here, electric intensity depends on lambda and r. Lambda is charge per unit length, r is the distance. So it depends. It depends only on distance. This is very important. Distance of the point of consideration. It depends on the distance of point of consideration. Okay? So that's it only. So I hope you understood this. Now we learn a problem based on second application of Gauss law. Now let me go through the problem and let's try to understand what they given. A charge of 5 into 10 raised to minus 10 Coulomb is given to thin metal cylinder, okay, of length 10 centimeter, placed in air. So you remember it's the air. Calculate electric intensity due to the cylinder at a distance 0.2 meter. This is the R, this is the L, and this is the charge. Okay? And we have to find out electric intensity. Now you can see the answer here. So charge is already given in Coulomb, 5 into 10 raised to minus 10 Coulomb. Length 10 centimeter that we have to convert. 10 into 10 raised to minus 2 means 10 raised to minus 1 meter, or 0.1 meter you can write. Radius, sorry, not radius, the distance of the point is 0.2 meter. Now, first we find out this lambda. It is linear charge density. So charge by length. So charge is this. After dividing by length, we get this value for linear charge density. Now electric intensity is E is equal to, you know that this formula is 1 upon 4 pi epsilon 0 2 lambda by r. This is the formula. Okay, same formula I written like this. And this 1 upon 4 pi epsilon 0, we substituted 9 into 10 raised to 9. 2 as it is. Lambda is this that we substitute here. Divide by this r, 0.2. And after doing the calculation, we get the answer 450 volt per meter. 450 volt per meter is the electric intensity at a distance 0.2 meter from axis. I hope you understood how we solved. One more thing you remember. So in a problem here, they given air. The cylinder is placed in air. If cylinder is placed in a medium of dielectric constant K, the same formula we can write for electric intensity, 1 upon 4 pi epsilon 0 K 2 lambda by R. So K we have to write. Then you can modify this formula like this, 1 upon 4 pi epsilon 0 like this, and multiplied by 2 lambda divided by K into R. And this value is 9 into 10 raised to 9. And this you can solve. Okay? You remember, if charges are placed in a medium of dielectric constant K, that time you have to use this formula. Now, let me learn next application. Next application is electric field intensity due to infinitely long, thin, plane sheet. You note here, it's an infinitely long, thin, plane sheet. ठीक है, charge plane sheet you can see. Now this is a plane sheet. Some charges are given to that, positive charges. Now sigma, you know that this sigma is what? Charge per unit area, surface charge density. Okay. Now to find out electric intensity, we consider this is a smaller part, smaller area. To find out electric intensity near this plane sheet, we consider this is a Gaussian cylinder. Pass through this smaller area of this plane sheet. Okay. We consider a smaller Gaussian cylinder whose radius is R, length is L. Okay. Now here electric intensity and area. This area vector is ds bar. The direction you can see. Electric intensity also you can see. Okay. At surface A. Okay. At this surface, this is the direction of electric intensity and area vector. Now I consider this portion B. The electric intensity and area vector, they are along same line. Now I consider another portion which is on this cylinder C. The electric intensity is away from positive charge. Everybody know that direction of electric intensity. And this area vector is perpendicular to that area element, that smaller portion. So this direction is perpendicular. So here angle theta is 90 degree. So here theta is 0 degree. So here also theta is 0 degree. Now by Gauss law, we have written formula. Electric flux is equal to integration over a closed path E bar dot ds bar is equal to q by epsilon 0. Now we have to find out this. So we have to find out this integration of E bar dot ds bar. In this integration we have to find out. Now we consider this three part A, B and C. So similar to the previous article. So this integration we can write. So the integration over the surface A, E bar dot ds bar, as well as for surface B and surface C. So we have written this addition. Now angle we know that. So at this point A 0, B is at B 0 and at C it is 90 degree. Okay. Let me substitute. So this left hand side as it is. Then at A we get integration E ds cos 0 because angle is 0. At B we get integration E ds cos 0. At C we get this term. Okay. Integration E ds cos 90. Cos 90 is 0. So this term get cancelled. Okay. So we get these two integration. And here cos 0 is 1. So integration E ds into integration E ds. 2 times integration E ds. So 2E we are taken outside because electric intensity on this Gaussian surface is constant. So electric intensity is constant, that taken out. Integration ds. And this ds is the area. Which area? This area basically. Let us highlight that area. So this area, and you can see this area is circular. So pi r square. So we can write this area is circular. So area is pi r square. You can see here pi r square. And this 2e as it is. So we get this. As well as by this formula of sigma, we get sigma is charged by ds. So here we substitute q is equal to sigma ds. We get q is equal to sigma ds, and this q we substitute here. Okay? And then we can equate this formula and this formula. ठीक है, we equate because you know that this is equal to this, we are using this equation. Now you can see in the next step. So by Gauss law, Q by epsilon is equal to, so we already discussed sigma is charge by area and area is pi r square. So Q is equal to sigma into pi r square that we substituted here. Okay. So we get Q by epsilon 0 is sigma pi r square by epsilon 0. And this is equal to integration of E bar dot ds bar. And this we are getting pi r square. This term we are getting pi r square multiplied by 2e. That we substitute now. Hence, instead of this term, we substitute this. Okay? And this term as it is. So we get this equation. Now in that equation, we have to cancel the common term. So common term we can cancel, pi r square get cancelled. So what we get? So we get 2e is equal to sigma by epsilon 0. So by that formula, we can write a formula of E. 2 we can shift to this right hand side. So we get this electric intensity is sigma upon 2 epsilon 0. Sigma upon 2 epsilon 0 is electric intensity. And this is expression for electric intensity near infinitely long charge plane sheet. The same equation we can write in vector form by writing unit vector only. Unit vector you can write anything. Anything you can write in unit vector. Now after that, so direction here. The direction of electric field intensity is normal to the plane. So normal to the positive charges basically. And away from positive charge distribution. For negative charge distribution, it will be towards the plane. But here in a diagram, we consider positive charge distribution. And again, the same note, electric field intensity is independent. This is important. Independent of size of Gaussian surface, we considered. Okay? It neither depends on, here you remember, it neither depends on distance of point of consideration, nor the radius of cylinder. Now here it does not depend on the distance of point of consideration. Now in the cylinder or in the wire, we learn it depends on the distance of point of consideration. But here it neither depends on distance of the point of consideration. You can see here electric intensity depends on this surface charge density and epsilon 0. Now here we finish the second application. Now if the plane sheet is thick, in the heading we consider thin plane sheet, thin. But we can consider this as a case 1. If the plane sheet is thick, then the charge distribution will be available on both sides. Then the charge distribution is available on both sides. So the charge enclosed within the Gaussian surface will be twice. So charge will be twice the before. Hence, if the charge is twice, then this sigma is also twice. So we get this electric intensity for this thick plane sheet is sigma upon epsilon 0. So here it is coming 2. So here 2 is missing here. If the plane sheet is thick, that also you remember. Now next, a problem based on this third application. Now let us explain what they given in the problem. The charge per unit area in sigma of large flat sheet of charge 3 3 microcoulomb per meter square, means this is a charge. Charge per unit area, charge upon ds, means this is given sigma. Okay? Surface charge density they given. So meter square, you can see here it is a unit of area. And microcoulomb is the unit of charge. Charge divided by area unit. Unit of charge divided by unit of area. Calculate the electric field intensity at a point just near the surface of sheet. So just near the surface of sheet and measure from midpoint. Now we know the formula, electric intensity due to infinitely long charge plane sheet. Now this sigma is given 3 microcoulomb per meter square. So that we have to convert. 3 micro means 10 raised to minus 6 coulomb, and this meter square as it is. So that is coming 3 into 10 raised to minus 6, that we substitute here. 2 as it is. Epsilon 0, you remember it's a constant and value is 8.85 into 10 raised to minus 12. So this is the value. After doing the calculation, we get the answer. After doing the calculation, we get answer here. Dear student, in today's lecture, we start article electric potential from chapter electrostatic. Now what is electric potential? You already use this word electric potential many times. So what is electric potential? So electric potential is basically a work done to bring a unit positive charge from infinity to a point in electric field. This is the electric potential. For example, if I consider one charge, let's say plus Q charge, and this charge plus Q having an electric field in its surrounding area. This circle represents electric field of this charge. Now within that electric field, if I consider this is the point A, and to that point, if you want to discuss what is electric potential at point A, so that time if I consider infinity distance, from infinity distance a unit positive charge, if you bring at point A, then some work is done, and that work done is nothing but electric potential. So work done to bring unit positive charge from infinity to point in electric field is the electric potential at this point. So infinity distance to point A, if you bring unit positive charge, work done in that case is called as electric potential. This electric potential is given by this formula, W by Q0. Unit, SI unit is joule per coulomb, or it is also called as volt. So dimension of work divided by dimension of charge. By solving this, we get the dimension for potential, L2 M1T minus 3 I raised to minus 1. So this is the dimension for electric potential. Now electric potential due to point charge. Electric potential due to point charge is given by formula 1 upon 4 pi epsilon 0 Q by R. This potential is given by formula 1 upon 4 pi epsilon 0 Q by R. If this charge is placed in free space or vacuum or in air, then this is the electric potential due to a point charge. After this, electric potential energy. Now, what is electric potential energy? So, electrostatic potential energy is the work done. It is work done against electrostatic force to achieve a certain configuration of charges. So, you know that work done and energy, they are equivalent. So, electrostatic potential energy is work done against the electrostatic force. Work done against the electrostatic force to achieve a certain configuration of charges. So basically, remember work done is the potential energy. Consider, now we consider one charge, positive charge Q. It is fixed. Positive charge Q is fixed at some point in space. For bringing any other positive charge close to it, work is done, which is equal to the potential energy. So you remember. So if I consider the positive charge Q, which is in the space, and to bring any other charge close to it, close to this charge, some work is done, and that work done is called as potential energy. Now here, a simple diagram you can see. If this is charge, okay, this is charge plus Q. And if we bring any other charge, for example, this positive charge plus Q0, closer to this charge, then some work is done. And that work done is nothing but the potential energy. Thus, we can write here the work done against electrostatic force is equal to increase in the potential energy. If you see, when we are bringing this charge in this direction, some work is done. Some work is done against the electrostatic force, F. So we written here work done against the electrostatic force is equal to increase in potential energy. So we get one formula here. So work done is force into displacement. If I consider that a charge is displaced from A to B, so displacement is dr. Electrostatic force is F. Okay? So we get increase in potential energy is equal to F into dr. This is the formula for increase in potential energy. So du is the increase in potential energy, dr displacement, and F is force exerted on the charge. I hope you understood this potential energy. Now, after this, our next article is expression for electrostatic potential energy. Expression for electrostatic potential energy. Now we consider a charge. Again, you can see in a diagram, charge plus Q is placed at point O. Okay? Unit positive charge plus Q at A. Okay? And this point A is at a distance R1 from this charge Q. Now consider the electrostatic field due to a charge plus Q. So we are considering electric field due to this plus Q charge. And the origin is O, means this charge is placed at point O. Now let small charge plus Q0 be brought from A to B. So this charge is brought from A to B. So this we have to bring from A to B. So distances are R1 and R2 from O. R1 and R2 are the distances of A and B from a charge. Work must be done against the repulsive force. Pay attention, both are positive charges, so repulsive force. Okay? And work must be done against that repulsive force. So here pay attention, work done to move a charge Q0 through a small distance dr. So first we find out work done to move a charge with a small distance dr against the electrostatic force Fe. So this is the dr is the small distance. We find out work done for that. Then we find out total work done to displace it from a distance R1 to distance R2. So we get formula work done is equal to force into displacement. So force is the electrostatic force, okay, and this into displacement dr. Now work done appear as increase in potential energy, and this work done appear as increase in potential energy. So just we already discussed in the previous article. So work done appear as an increase in potential energy. Now same equation we are written like this. du is the increase in potential energy is equal to minus Fe into dr. So now I'm not written vector form here. So you can see here it is F bar and dr bar is written. But here I written directly minus sign. Minus sign indicates that this work is done against the restoring against the electrostatic force. So because of that minus sign is coming. Okay? Or you can say, so this Fe and dr, so they both having opposite directions. So this is the direction of electrostatic force and displacement is opposite to that. Okay? Negative sign shows that displacement dr against electrostatic force. For the displacement of charge from initial position A, for displacement from initial position A to the final position B, the change in potential energy, pay attention, for a displacement of charge from initial position A to B, change in potential energy can be obtained by integrating this. If we integrate this equation, then we get the change in potential energy, total change in potential energy. So integration within limit we have to do because we have to displace the charge from this R1 to R2 only, A to B. So we can write here. So change in potential energy is equal to integration of du within a limit R1 to R2 because we have to displace a charge plus Q charge, Q0 charge from point A to B, means from distance R1 to from distance R2. And both the distances are measured from the same point O. Now we substitute here du. So we get minus integration Fe dr. So this formula we get. The electrostatic force between two charges separated by distance r. Electrostatic force. And the electrostatic force we get by Coulomb's law. We get electrostatic force by using Coulomb's law. जो Coulomb's law हमने इससे पहले already learn किया था. So what is the electrostatic force? Electrostatic force is 1 upon 4 pi epsilon 0. First charge multiplied by second charge. Okay, first charge is capital Q. This charge is Q0, small q0. divided by distance is r square. If the distance of separation between these two charges is r, then electrostatic force is given by this formula. Okay? So this is the electrostatic force. Now, after that, for a system of 2-point charge, for a system of 2-point charge, so increase in potential energy is equal to, I written this again. So this is the electrostatic force that we have to substitute. And after substitution, we get this formula. We get this formula. We substitute only here electrostatic force. Electrostatic force we substitute. Now we have to simplify this. Now this 1 upon 4 pi epsilon 0 is constant, q into q0 is constant, so integration 1 by r square dr. Okay. Then integration, this integration 1 by r square dr is minus 1 by r. This integration is minus 1 by r. And if a limit is there, r1 and r2, we have to put the limit now. Okay, so we are written here the integration. So this minus multiplied by minus is plus. Okay. Now we substitute the limit. Now instead of doing this minus into minus plus, otherwise we can do it minus multiplied by minus plus and we substitute the limit. Okay. So or we can write the another step here. Pay attention. 1 upon 4 pi epsilon 0 minus wala. Then q into q0. Okay. Minus 1 by upper limit we have to substitute, which is r2. Okay. Then minus and this minus minus plus 1 upon r1. Okay. We get this. Then if you take a minus common from this, then minus plus. So 1 upon 4 pi epsilon 0. So q0 1 by r2 minus 1 by r. So this equation, you can see the same equation is written here. Okay, this is the basic mathematical steps that you already learn. या आपको मैथमेटिक्स में ऐसे स्टेप्स आपको लर्न करने हैं. दिस इज सिंपल इंटीग्रेशन. जो मैथ्स में इंटीग्रेशन आपको लर्न करना है, दैट टाइम यू फाइंड इट इज वेरी इजी. ठीक है. नाउ this is the increase in potential energy. This is increase in potential energy. The change in the potential energy or increase in the potential energy depends only on the end point and is independent of actual part taken by the charge. Pay attention. This is very important. Change in potential energy depends only on end points and is independent of the actual path taken by the charge. It is independent by actual path. Means how the charges are displaced from one point to another point. Based on that actual path, it is independent. So it depends on only the end points. So here you can see here R1 and R2 is mentioned. So point A and point B, these are the points. Okay. Now, I hope you understood this derivation. Now pay attention. So this work done to displace from point A to B is equal to this change in potential energy. So this work done is equal to the change in potential energy. And the change in potential energy formula is already known. So work done to displace a charge from A to B is given by this formula. Okay? It is convenient to choose infinity to be the point of zero. It is convenient to choose infinity to be the point of zero potential energy. Means at infinity we are considering zero potential energy. As the electrostatic force is zero at distance infinity. Why we are considering this is zero? Because distance is infinity. So the potential energy is zero. Electrostatic potential energy of system of two charges Q1 and Q2 separated by distance r can be obtained. Now let me consider here at infinity potential energy is 0. Now here we can write electrostatic potential energy which are separated by some distance r. Electrostatic potential energy between two charges separated by distance r can be obtained by. So means here r1 distance I substitute infinity and r2 is equal to r. It is the distance between two charges r. Okay. Then we get a formula, and this is the final formula for electrostatic potential energy. You remember this formula. Electrostatic potential energy is given by formula 1 upon 4 pi epsilon 0 Q1 Q2 divided by R. This is the potential energy formula. Now we write this formula for several cases. So different cases we have to consider for this formula. Now this unit of potential energy. So you know that energy having a unit joule. So obviously this electrostatic potential energy also measured in joule. So you remember one thing here, 1 joule means how much? 1 joule is the energy stored in moving a charge 1 coulomb through a potential difference 1 volt. 1 joule is the energy stored in a charge of 1 coulomb through a potential difference of 1 volt. Another convenient unit is electron volt. This electron volt unit is also unit of energy. Okay, we can represent this potential energy in electron volt, and which is the change in kinetic energy. What is the electron volt? Electron volt is the change in kinetic energy of electron while crossing 2 points which are maintained at potential 1 volt. If 2 points A and B maintain at 1 volt, okay, and if electron cross these 2 points, then kinetic energy of the electron is called as 1 electron volt. So remember one thing here, conversion. 1 electron volt is equal to 1.6 into 10 raised to minus 19 joule. Okay. Instead of electron volt, if it is milli electron volt, 1 milli electron volt is equal to how much? 1.6 into 10 raised to minus 22. You know that this milli means 10 raised to minus 3. So minus 19 minus 3 minus 22, you can see. Now what is concept of potential? Just we have to learn this concept of potential. We already learned potential energy of two particle system 1 upon 4 pi epsilon 0 Q1 Q2 by R. This is the potential energy for two particle system which are separated by a distance R, and potential energy is given by this. Now same formula we can write like this. We are taken Q2 outside, or the same formula we can write by taking Q1 outside. Okay, same formula by taking Q1 outside. Now here this quantity Q1 upon 4 pi epsilon 0 R is the potential, is the electric potential. So let me represent it by V, or V in a bracket R. And this quantity depends on charge Q and location. We already learned it is independent on the path. So same equation you can write, this equation you can write, this is potential V1 R into Q2. because it's a charge q1. Similar manner, we can write it v2 r q1, and you can see they are equal. Here we are written same formula in different way only. Okay. So this electrostatic potential energy, we can write in this format also. U is equal to potential into charge. You can see here, you already seen, this is a potential and this is a charge. Okay. So we are written formula, electrostatic potential energy is equal to potential V into charge Q. V into Q, this is the formula. So electrostatic potential we can write. So this is the formula. You can see here, this is the formula for electrostatic potential. Okay. Electrostatic potential is electrostatic potential energy per unit charge. If you see this formula and this formula, okay. So only one charge is missing here. So electrostatic potential energy per unit charge. If we divide this potential energy by charge, we get electrostatic potential. So we get this formula. Just in the beginning, I told you electrostatic potential is, work done to bring a charge. And that work done is nothing but the electrostatic potential energy. So electrostatic potential difference between 2 points is, so you can write the potential difference by this formula. So this is the potential difference. So difference in the two potential. So difference in the two potential energy divided by charge. So we can write potential difference is given by this formula. Electrostatic potential difference. In that formula, V2 minus V1 is the work done per unit charge to move charge from point 2 to point 1. So listen. Next one is relation between electric field and electric potential. Relation between electric field and electric potential. Electric field means electric field intensity E, and electric potential means electric potential V. Relation between E and V, that we have to find. So we consider the electric field produced by charge plus Q kept at point O. We consider electric field produced by charge plus Q kept at point O. Now we consider diagram. So this is the point O. At that point O, we have to place a plus Q charge. And this is the direction of electric intensity. Electric intensity is directed away from this positive charge. This electric intensity is directed away from positive charge. Now, एक मिनट. Now we consider point M and N, which are separated by distance dx. The distance between M and N is dx, and this charge is plus Q. At point M, we consider a charge Q0 is placed. Q0 is what? Unit positive charge. What is unit positive charge? Unit positive charge means whose value is 1 coulomb. Okay? And this is direction of electrostatic force acting on this charge. Electrostatic force acting on this charge is, this is the direction. Now, the work done to move unit positive charge Q0 from point M to N means we have to displace this charge from point M to point N with a small distance against the electrostatic force or against the direction of electric intensity, and that work done is given by formula minus F into dx. Again, minus sign indicate that F and dx, they are oppositely directed. You can see here, this is electrostatic force and we are displacing the charge opposite in opposite direction. Now, this F is equal to Q0 into E. So how we get this? You know, electric intensity. Electric intensity is force acting on unit positive charge. So we can write F is equal to Q0E. This is the formula. So by this formula, we get work done is equal to minus Q0E into dx. So we shift this Q0 to left hand side. So dW by Q0 is equal to minus E into dx. These are the mathematical steps. I hope you understand. But dW by Q0 is potential difference. Potential difference between these 2 points. In the previous article, we already learned potential difference. Okay? Now we substitute. Hence, dV is equal to minus E into dx. Now we transfer dx to this side. dV by dx is minus E. Now we can write formula of E. And this is the relation. This is a relation between electric field and electric potential. So these are the easy steps that you have to remember. And this, you remember, this dV by dx is called as potential gradient. So this dV by dx is called as potential gradient. So we can write here E is equal to minus potential gradient. Thus, the electric field at a point in electric field is negative of potential gradient at that point. Hello everyone. We have to learn what exactly the word zero potential indicates. So the potential at point A in electric field is the amount of work done to bring a unit positive charge from infinity to point A. So potential at any point, we already know what is the potential at point A. So it is the work done to bring unit positive charge from infinity to that point is the potential at point A or at that point. The nature of potential is such that its zero potential is arbitrary. Once the 0 point of the potential is set, then every potential is measured with respect to that reference. The zero potential we have to set. And every potential we are measuring with respect to that zero potential. In case of point charge, if I consider single point charge or collection of charges, the zero potential is at infinity. Zero potential is set at infinity. Means at infinite distance, potential is 0. For electrical circuit, the earth is usually taken to be 0 potential. For electrical circuit, the earth is usually taken to be 0 potential. Okay. You remember? So here simple conclusion. We are measuring potential with respect to the point, and that point is called as a 0 potential point. And generally for point charges, 0 potential point is at infinity. I hope you understood this 0 potential article. So it's not much more things to remember here. Now after that, a new article, and it is electric potential due to a single point charge. Electric potential due to a single point charge. Now we consider the electric field produced by a charge plus Q kept at point O. Now let me show this point charge in a diagram. So you can see here, so this is the point charge plus Q. It is placed at point O. This is the direction of electric intensity. You know that electric intensity is directed away from positive charge. So this is the direction of electric intensity. Now we consider a unit positive charge, Q0. This Q0 is what? Unit positive charge. Now unit positive charge means, so this charge having a magnitude 1 Coulomb. A unit magnitude. Unit positive charge plus Q0. It is placed at one particular point. Okay. Then force acting on this unit positive charge. Force acting on unit positive charge is, it's a repulsive force. So away from this plus Q charge. So you can see in a diagram, this F represent force acting on this unit positive charge Q0. So this is infinity distance. This is infinity distance. Okay. Now, I consider the point charge Q0 is at point M, which is at a distance x from the point O or from the charge plus Q. Now, more 2 points we consider N and A point. This point A is at a distance R from the charge plus Q. You can see in the diagram, small r is the distance of point A. The distance between these two, M and N, is dx. Distance between M and N is dx. Dx is the distance. Now we have to find out the electric potential at point A. At point A, we have to find out electric potential. Now just we learn electric potential is what? Work done to bring a unit positive charge from infinity. And this is the infinity distance. Means we have to consider Q0 here. And this Q0, we have to bring it to the point A. Then some work is done. And that work done is nothing but the electric potential at point A. Okay. To find out that work done, initially, we can consider this unit positive charge Q0 is placed at point M. Then we bring it to point N with some distance dx. And then we find out that smaller work done. We find out smaller work done to move a charge from M to N. And then total work done we get by integrating the equation from a limit infinity to R. Okay, from infinity distance to distance R, we have to displace unit positive charge. So whatever the work done we get in this case, To displace a charge, unit positive charge from M to N, we integrate that within the limit. Now, the electric potential at a point A is amount of work done per unit positive charge, which is displaced from infinity to point A. Now, the electrostatic force on unit positive charge at M is, electrostatic force we can write by using Coulomb's law. So this is the first charge, this is the second charge. Okay? And by we have to find out, and distance between these two charges is x. Then electrostatic force is given by formula F is equal to 1 upon 4 pi epsilon 0. These charges are in free space. So 1 upon 4 pi epsilon 0 is constant. First charge Q, second charge Q0 divided by x square. Divided by x square. This is the electrostatic force. Now you remember one thing here. This Q0 is unit positive charge. This Q0 is unit positive charge. Means Q0 having value 1. So it's a unit positive charge. So Q0 is 1. So let me substitute this Q0 as a 1 in the equation. So we get F is equal to 1 upon 4 pi epsilon 0 Q by x square. So this is the equation number 1. So this is the equation number 1. For infinitely small displacement dx, we have to consider this dx is very small displacement. From M to N, amount of work done. For displacement of charge from M to N, the amount of work done. Work done is what? Force into displacement. Okay? So force is this, electrostatic force, and displacement is how much? Dx. So we can write work done is equal to force into displacement. Force is F, displacement dx. So the negative sign indicates that this F and dx, they are oppositely directed. Negative sign indicate that F and dx are oppositely directed. So you can see in a diagram also. The direction of F, this is the direction of F. And we displace unit positive charge from M to N. So these two directions are opposite to each other. So we written here a negative sign. Now, we have to substitute the formula, this F we have to substitute in this equation. Then we get the work done. Then we can integrate. Otherwise, first we find out total work done and then we substitute F. So total work done in displacing unit positive charge from infinity to point A is. So we find out total work done to displace a charge from infinity to point A. So total work done. So total work done we can write by using a formula, integration of this equation 2. But we have to displace a charge. We have to displace charge from infinity to point A. We have to displace charge from infinity to A. And because of that, limit is infinity to R. So point A is at a distance R. So we are written limit here. So limit infinity to R and minus F dx. Now we have to substitute this formula. This formula of F we substitute in the formula of work done. So we get W is equal to integration infinity to R. This minus sign as it is. This F, this is the value of F. 1 upon 4 pi epsilon 0 Q divided by x square. And this dx as it is. Okay. Then the constant we have to take it outside. So Q is a charge which is constant. 4 pi epsilon 0 is constant, so taken outside. So integration 1 upon x square dx. So this 1 upon x square is written x raised to minus 2 dx. This is a basic mathematical step. And then we have to use a formula of integration. Now let I tell you which formula we have to use. X raised to n is integration of x raised to n dx is x raised to n plus 1 divided by n plus 1. This is the formula. And this formula we have to use here. We have to use the formula of integration here. Now by using that, we can write. By using this formula of integration, we can write now. So this integration is coming minus 1 by x. How it is minus 1 by x? So if you use this formula, x raised to minus 2 plus 1 divided by minus 2 plus 1. Minus 2 plus 1 is minus 1. So you get here x raised to minus 1 divided by minus 1. It means that you can write like this, minus 1 by x. It is minus 1 by x. And this limit infinity to r as it is. Now we have to substitute limit. So W is equal to Q upon 4 pi epsilon 0. So instead of this x, initially we have to write r, this upper limit. So we get minus 1 by r. Minus 1 by r. Then we have to put minus sign and then minus 1 by infinity. Or we can write here this minus q upon 4 pi epsilon 0 as it is. Then minus 1 by r minus minus plus 1 by this infinity. Now this minus sign we can take common. This minus into minus plus, here it is plus. So we can write q upon 4 pi epsilon 0. 1 by r minus 1 by infinity, because we have taken minus sign common. So minus 1 by infinity. So 1 by infinity is 0. So this get cancelled in the next step. So we get W is equal to q upon 4 pi epsilon 0 multiplied by 1 upon r. So this is the formula of work done. So work done. Again, same formula is written, and we have to substitute this 1 by infinity is 0. So 1 by infinity 0, it means that work done is given by formula 1 upon 4 pi epsilon 0 q by r. So this is the work done. And you already know that electric potential electric potential is what? It's a work done to bring a unit positive charge from infinity to a point A. Okay? So we can write by definition of electrostatic potential at A due to charge Q. We can write electric potential is equal to work done. Potential is equal to work done. So you remember here that I tell you, so electric potential is work done to bring a unit positive charge. So this is the formula of electric potential. But here Q0 is unit positive charge, so its value is 1. So we get a formula. Electric potential is work done. So let me substitute here. We substitute. So V is equal to 1 upon 4 pi epsilon 0 Q by R. This is expression for electric potential at any point in electric field due to a point charge. Now let me consider here. So this is the electric potential. One more thing let I tell you. In the previous articles, we already obtained electric intensity also. Now electric intensity is given by formula 1 upon 4 pi epsilon 0 Q by R square. So this is the electric intensity. So here This is electric field intensity and this is electric potential. Okay? So you can see here EV. And this is the distance. You can see the relation. V inversely proportional to R. This is the relation. And E inversely proportional to distance square. This is the relation. And if you plot a graph with the distance, means graph of electric intensity or electric field and graph of electric potential with the distance, we get this type of nature. Okay, it means that as distance increases, this both E and V decreases. You can see here as we increase the distance, this V start decreasing as well as E start decreasing. And the relation you can see here, the relations. So V inversely proportional to this and E inversely proportional to this 1 by R square. Means this is the relation. I hope everybody know this relation and understood what exactly I want to say here. Now we have to remember some point here, as well as I will tell you one more formula here. Electrostatic force. Electrostatic force. So 1 upon 4 pi epsilon 0 Q into Q0 divided by X square or R square. Okay, Q0 is unit positive charge here. So F inversely proportional to R square. So this is the relation. Now, due to single charge at distance R, due to single charge at distance R, the first relation for electrostatic force, the electrostatic force is inversely proportional to distance square. Second relation we can write about electric intensity. So here we already discussed electric intensity inversely proportional to this distance square. And the third one, potential. The third one is potential. So you can see here the relation V inversely proportional to R. So this is the relation. So here if we consider a one spherical object and charges are uniformly distributed over that. So this is a charge sphere basically, whose radius is capital R. Now we already learned Gauss law application for the sphere, and in that we learn for inside point electric intensity is 0. For inside point electric intensity is 0. And you remember one thing here, and for inside point V is equal to constant. For inside point V is constant. Okay, if it is a charge spherical body, so inside point electric intensity 0 and electric potential is constant. So that constant value may be anything, it depends. So you can see here this electric intensity graph. So here from this point we get some electric intensity. Means if we consider, so this is spherical surface. If we consider this is a spherical surface, it's a charged spherical surface. Now from this origin to this a point on the circumference, okay, this electric intensity is 0, okay, in this region. And then as we cross this point, the electric intensity start decreasing. So here it is maximum and then it start decreasing. So from graph it is clear. But V, We cannot say for inside point it is a 0. It is a constant. Whatever the value it has, it is a constant. And again, as distance increases, it start decreasing. After this, electric dipole. Electric dipole. So basically, di means 2 and pole means charges here. It's an electric dipole. So di means 2, pole means charges. So electric dipole is pair of, it is pair of equal and opposite charges separated by very small distance or separated by finite distance. Electric field produced by dipole is known as dipole field. It is known as dipole field. Electric dipole moment is a vector quantity. You remember, it is a vector quantity used to measure strength of electric dipole. Electric dipole moment is vector quantity. Electric dipole moment is vector quantity and used to measure strength of electric field. Now we consider two charges. So this is minus q and this plus q charges. So here we consider both the charges must be equal. Opposite. Opposite means if one charge is minus, another charge is plus. So you know that there are two kind of charges, minus charge, negative charge and positive charge. So we consider opposite charges. If they are separated by some distance, 2L. So distance of separation between two charges is 2L. You can see in a diagram. Then electric dipole moment. Generally electric dipole moment we represent by symbol P. Electric dipole moment having a direction minus q to plus q charge. You can see in a diagram the direction of electric dipole moment. Electric dipole moment is given by formula. Electric dipole moment is given by formula. Q multiplied by 2N. Q is what? One charge, positive charge generally we consider. Multiplied by 2L. 2L is what? Distance between two charges. So this is a vector form, or you can write P is equal to Q multiplied by 2L. So this is the formula of electric dipole moment. Okay, again, so here we are written in detail. Magnitude of electric dipole moment is product of magnitude of either charge and distance between two charges. So you know that why we use either charge. Either means both the charges are equal, obviously. Only the this one is positive and one is negative. Magnitude wise both the charges are same. So here magnitude we are considering. Magnitude of electric dipole moment is product of either charge and distance between two charges. So this is the formula. The direction is from negative to positive charge. So that we just discussed. SI unit of electric dipole moment is, SI unit of electric dipole moment is, the formula is Q into 2L. Unit of Q is Coulomb, 2L is a distance, so unit is meter. So Coulomb multiplied by meter is the unit. Coulomb meter is the unit of electric dipole moment. Hello everyone. In today's lecture, we start article electric potential due to an electric dipole. Electric potential due to an electric dipole. In previous article, we already obtained electric potential due to point charge. ठीक है? Due to point charge, electric potential is 1 upon 4 pi epsilon 0 Q by R. This is the formula for electric potential due to point charge. Now we have to use this formula. Now pay attention. We consider an electric dipole AB consisting of two charges plus Q and minus Q separated by finite distance 2L. So this is L. It is separated by a finite distance 2L. You can see it in a diagram. Now here, let C, capital C, you can see here C, be a point near electric dipole. So this is the electric dipole. See here, this is the electric dipole. So this is a plus Q charge, this is a minus Q charge, and this is a point C, which is at a distance R, which is at a distance R from center of dipole. Center is O. Okay, and incline at an angle theta. You can see the angle of inclination here. So this angle is the theta. R1 and R2, this R1 and R2, these are the distances of point C from plus Q and minus Q charge. R1 and R2 are distances. R1 and R2 are distances from charge plus Q and minus Q respectively. Okay. Now we have to find out electric potential at point C due to this dipole AB. So this dipole is, AB is the dipole, and due to this dipole, what is the potential? Due to single charge, you know that how much is the potential. Now here the two charges are there. Dipole means two charges, and due to these two charges, how much is the electric potential? That we have to find out. Now potential at point C due to plus Q charge. Potential at point C due to plus Q charge is, again, plus Q charge is placed at point A, and it is given by formula. V1 is equal to, so due to this charge plus Q, the potential we represent by symbol V1. V1 is equal to Q upon 4 pi epsilon 0 R1. R1, why R1? Because distance of the point C from charge plus Q is R1. You can see this distance R1 in a diagram. Okay. Similarly, so this is due to plus Q charge. We can find out potential at point C due to minus Q charge. So that time distance is R2. You can see the distance is R2 that time. So potential at C due to charge minus Q, and this minus Q charge is at point B, and it is given by formula V2 is equal to, so V2 is equal to minus Q, because the charge is minus Q, minus Q upon 4 pi epsilon 0 R2. So here we get formula for potential at point C due to plus Q charge and due to minus Q charge. यार कोणाचा आवाज येतोय? माझा माहित नाही झालं. ठीक है. Potential at point C due to plus Q charge and minus Q charge we are written by V1 and V2. Now The total potential at point C we have to find out. We have to find out total potential at point C. Now total potential is what? Addition of these two potentials. It gives us total potential. So the potential at C due to dipole is, the potential at C due to dipole is, so potential at C I use V subscript C is equal to V1 plus V2. So this is V1 and this is V2. Okay, now we substitute V1 and V2. So after substituting this V1 and V2, we have taken the common term. What is common? Q is common, 4 pi epsilon 0 is common, that we have taken outside. So only this R1 and this R2 is different. So 1 by R1 minus 1 by R2. Why minus? Because here in a formula of V2, minus sign is there. So minus 1 by R2. Now by geometry, we have to find out R1, R2, and then we have to substitute these values, and then we have to simplify this equation. Otherwise, you can remember one thing here. We can find out directly 1 by R1 minus 1 by R2, this bracket, and we substitute in this formula. Now how we find out this R1? You can see in a diagram R1 and this is R2. Okay. So here, so below that we extended this line for that purpose only. So this, we are written L sin theta, we are written this distance L. Okay. Because of we have to use cosine rule here. We are not use this L sin theta is not useful here. Okay. Now pay attention, we have to use cosine rule. You may learn cosine rule in mathematics. You already learn cosine rule in mathematics. That cosine rule we have to use. Now by cosine rule, see the diagram very carefully. I can write here R1 square. So this R1 square is equal to, so this R1 square is equal to this R square plus this L square minus 2RL cos theta. So this is the formula of R1 by using cosine rule. You already learned cosine rule in mathematics. Okay, so by that rule we get this R1 square is equal to. Now from that we can take R square common from every term. So from this equation we can take R square common. So as we take R square common, we get the term 1 plus, so this is taken outside, 1 plus L square by R square minus 2 L by R cos theta. So this formula we get after taking this R square common. As we take R square common, we get this formula. Similar manner, when we are finding R2, so that time you have to remember instead of this minus sign, only the plus sign is there by using cosine rule. By using cosine rule. Now R2 square is equal to, R2 square is equal to R square plus L square plus 2RL cos theta. Again we take here R square common from right hand side. Then we get a term in a bracket 1 plus L square by R square plus 2 L by R cos theta. So this term we get. Now here for short dipole, this you can remember. This distance L is very, very small as compared to R. Distance L is very small as compared to R. If L is smaller, obviously L square by R square you get smaller quantity. If it is a smaller, we neglect that. For short dipole, this L is very, very small as compared to R. So we neglect L square by R square. Okay, this L by R is a small, so L square by R square is more and more small, so we neglect that. So after neglecting that, we get R square is equal to, as well R1 square is equal to, as well as we can write this R square, okay, R1 square we get by this formula. Then by using that we can write R1 is equal to, we can take whole thing in a root, or square root of R square is coming R, and this bracket raised to 1 by 2 means the square root of this bracket. So 1 minus 2L by R into cos theta raised to 1 by 2, raised to 1 by 2. So this is the R1. Similar manner, by using this formula we can write R2 by eliminating this term. So also R2 square is equal to R square 1 plus 2L by R into this cos theta, into this cos theta. Okay. Now by using that we can write R2 is equal to, in a similar way we can write R2. R2 is equal to R 1 plus 2L by R into cos theta raised to 1 by 2. So we are written here R1. So we get here R2. Okay. We get R1, we get R2. Now we can find out 1 by R1, because we have to find out the term 1 by R1 minus 1 by R2. This term we have to find out. So we can write 1 by R1 is equal to, so this is R1. So 1 by R1 is, okay, we get like this. 1 by R in a bracket 1 minus 2L by R cos theta raised to minus 1 by 2. Means here we are written reciprocal of this, and we have changed the power here. You can see here minus 1 by 2. So that's why you can see same bracket here. Otherwise you can write 1 upon this bracket if you want to keep the power same, 1 upon this. So instead of that we are written minus raised to minus 1 by 2. Similar manner, 1 by R2 is, so this is R2. So 1 by R2 is equal to 1 by R, 1 plus 2L by R into cos theta raised to minus 1 by 2. Okay. Now we substitute this in a formula of this potential, total potential. So we get total potential at point C is equal to this Q upon 4 pi epsilon 0 is as it is. In a bracket 1 by R1 in this term, 1 by R1 minus 1 by R2. So this 1 by R1 is this, and 1 by R2 is this. We can take subtraction of these two. So you can see here, this term is written here, and this term is written here. So subtraction of this. Now we have to simplify this equation to get the final formula for potential at point C. Okay, by using binomial expansion. See here, maybe again the mathematics is involved, and you already learned a binomial expansion article in mathematics. So I'm not going in too much detail. So you remember here, 1 plus x raised to n is given by this formula. 1 plus the power multiplied by x. And here x is very, very small as compared to this L, means maybe this L may be there here. Okay, if x is very small, then the higher order term of the x we are not considering. Pay attention here. So that is not only the equation, we have to write some higher order term also. But that higher order term of this L by x or L by R, so that higher order term we are neglecting. Similar manner here in this equation, if you use binomial expansion, okay, we retain only the terms of L by R. So we are not keeping the term of L square by R square, L cube by R cube, that term we are not keeping. We are maintaining or retaining the terms of L by R only. We are retaining the term of L by R. Now, So we get the formula by using binomial expansion. So Q upon 4 pi epsilon 0, this 1 by R and this 1 by R we are taken outside. Now 1, this 1 as it is. This power multiplied by this term. Then 2 get cancelled. Okay, we get L by R cos theta. And this minus multiplied by this minus, minus minus plus. So you can see here the plus sign. Then this minus sign as it is here. Then 1, this minus 1 by 2 multiplied by this term. 2 get cancelled. And this plus sign change into the minus. You can see here the minus sign. You can see here the minus sign. Minus L by R cos theta. Now, after more simplification, this 1 and this minus 1 get cancelled. This L by R cos theta plus L by R cos theta is 2L by R cos theta. It is 2L by R cos theta. Okay. Now this plus 1 minus 1 get cancelled. And we get the term 2L by R cos theta. Now, after that, we rearrange the term. You can see here this Q multiplied by 2L. You know that Q multiplied by 2L is electric dipole moment. Okay? So Q multiplied by 2L is P. So that P we are written here. Okay? So 1 upon 4 pi epsilon 0, this P into this cos theta divided by this R and this R square. So this is electric potential at point C. So this is the important formula. That formula you have to remember. This is the final formula. Now, you can write this formula in different format also. Now we write in different format. So pay attention. We can write the same formula like this way also. So 1 upon 4 pi epsilon 0 P bar dot R bar divided by R cube. You can check here. It's a R cube here and here R square. So what's the why here R cube? The reason is, pay attention. Let I tell you, this formula we can expand like this: 1 upon 4 pi epsilon 0. P bar dot R bar is what? P into R into cos theta divided by R cube. Then this R and this 1 R from R cube get cancelled. So again you get the term. Same term you get. You get R square here. So which is similar to the previous equation. Okay. Now this formula we can write in that way also. Or when we are writing in vector form, that time we are writing the unit vector. So you can remember in that way also. Okay. So when we write a unit vector here, so unit vector this unit vector we are written. Unit vector is vector divided by magnitude. Then it is coming this R and this R square coming R cube. So that you can remember. Okay. Now pay attention. After this, we can write some special cases for this equation. Special cases when the point is an axial point. So what do you mean by the axial point? Means, pay attention. So this is a plus Q charge. This is a minus Q charge. Okay. And the point C is here. Now here we consider the point C is here. But if the point C is at this point, means, so this is the axis. So this is the axial point. If point C is the axial point, this is the case 1. Second case we have to consider, this is the center. And if we draw perpendicular, this point is, if the point C is here, means the point C is equatorial point. So equatorial point. That time, what is the formula for this potential? That also we have to learn. Now pay attention, let me learn about this. when the point is axial point. When the point is axial point, that time I told you here, one charge is here, one charge is here, and the point C is here. Okay? Then angle is 0. So no angle. Or this C point, if we consider on this side, then angle may be 180. Means possibility is either theta is 0 or it is 180. Okay? It is 0 or 180. Then if we substitute this theta is 0 in this formula, if we substitute 0 in this formula, cos 0 is 1, cos 0 is 1, so this term is 1. So we get 1 upon 4 pi epsilon 0 p by r square. And if I substitute 180, so here cos 0 is 1 and cos 180 is minus 1. Cos 180 is minus 1. If we substitute here cos 180, then minus 1, then here only the minus sign is coming. Okay? So let me write, after substituting these two thetas, the possibility of the potential is, this. So V axial is equal to plus minus 1 upon 4 pi epsilon 0 P upon R square. So this is the formula, plus minus, you can see here. So why we written plus minus? When the angle is 0, that time it is coming plus. When it is 180, it is coming minus. Okay, so this is the formula for potential at axial point. And you remember, for axial point, potential is maximum. Now case 2. Case 2 we have to consider the potential at an equatorial point. When the point is equatorial point, means if this is center O and this is point C, so that time this angle theta is 90 degree. Okay? When this point is equatorial point, theta is 90 and potential we get 0. So why this potential is 0? Because cos 90 degree is 0. Cos 90 is coming 0. And cos 90 is 0, and because of that, this potential is coming 0. Potential at equatorial point is minimum, means 0. I hope you understood this derivation. Electrostatic potential due to a system of charges. Okay. We learn potential due to point charge. Now potential due to dipole. Now potential due to a system of charges. Means potential due to single charge. And that potential due to single charge, means single point charge, we get 1 upon 4 pi epsilon 0 q by r. Potential due to dipole, we get 1 upon 4 pi epsilon 0 p cos theta divided by r square. Now potential due to system of charge we have to learn. Listen, for electrostatic potential, we already done these two. Now we have to start due to system of charges. For that we consider n number of charges. Consider this is charge 1, charge 2, this is charge 3, dot dot, charge 4, charge 5, charge 6, dot dot dot, charge n. N means Qn. This is nth charge. Now their distance from a particular point, the distance of the charges, are R1, R2, this is R3 and Rn, from a common point at which we have to find out potential. And pay attention, we have to find out electrostatic potential at point P due to this system of charges. At point P, we have to find out potential due to this system of charges. Now, in previous article, so due to dipole, we find out due to first charge, due to second charge, we add these two, we get the total potential. Similar manner. So we find out potential at point P due to charge 1, then due to charge 2, then due to charge 3, then due to charge 4, 5, 6, due to charge n. And then we add all the potential. So we get potential due to system of charges. So here we considered here the charges are Q1, Q2, Q3, dot, 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 Qn. These are the system of charges. R1, R2, R3, dot, 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 Rn. They are the distances of the charges from point P. Now the potential V1. The potential V1 at point P due to charge plus Q1. The charge Q1. The potential formula, you know that potential formula is 1 upon 4 pi epsilon 0 Q by R. This is the potential due to single charge. So we have to use this formula. So we get 1 upon 4 pi epsilon 0 Q1 by R1. Okay, this is the potential due to charge 1. Similarly, potential due to charge 2. It is coming 1 upon 4 pi epsilon 0 Q2 by R2. Potential due to charge 3 is V3. Okay. Similarly, potential due to charge n, nth charge. Now, the resultant potential by superposition principle. The superposition principle you already learned in the 11th standard. So by superposition principle, total potential due to system of charge at point P is addition of individual potentials. So we get V1 plus V2 plus V3 plus dot 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 plus Vn. Now we substitute V1, V2. So this is V1, this is V2, V3, V4 dot 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 Vn. We substitute these formulas here and let's see what we get. So you know that here 1 upon 4 pi epsilon 0 is common everywhere. So we can take directly, it is common. So 1 upon 4 pi epsilon 0 in a bracket directly. Q1 R1 in this, Q2 R2, Q3 R3. Okay, plus dot 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 plus Qn Rn. So this is the after substitution and taking this term common. This same formula we can write like this. We can write potential is equal to 1 upon 4 pi epsilon 0 summation of Qi divided by Ri. Or we can write like this. Same equation. Okay. Now in this equation, you can see here summation Qi divided by R. This I running from 1 to n. The value of I is changing from 1 to n. That you remember. So this is the electric potential due to system of charges. I hope you understood this article. Now we have to learn one example on the electric potential. The potential at point, let's see the example. The potential at point A in a space is given by this. So this is the potential at point A. Okay? And we have to find work done. Find work done in bringing a charge 3 microcoulomb from infinity to point A. And you know that work done to bring a charge from infinity to point in electric field is the electric potential. Means here we have to find out electric potential in the point 1. Okay. So see what the given here. So potential V is given. How much is the V? 4 into 10 raised to 5 volt. Charge is 3 microcoulomb. Q0. Micro means 10 raised to minus 6. So we converted 3 into 10 raised to minus 6 coulomb. This microcoulomb to coulomb. Now work done bringing the charge from infinity to point A. This is the work done. You know that potential is what? Work done to bring a unit positive charge from infinity to point in electric field. So by using that, work done is equal to V into Q. Q0. So here the charge is 3 microcoulomb that we converted into the coulomb multiplied by V. After doing this multiplication, we get the work done. So we get this formula, and the answer for this is coming 1.2 Joule. This is the work done to bring a charge 3 microcoulomb from infinity to point A. Now the second question, does the answer depends on the path along which charge is brought? So we know that this work done or the potential does not depend on this path. So no. So the answer is no. The work done is independent of the path. The work done is independent of the path. So in an article, electric potential, we learn the electric potential does not depend on the path followed by the charge. It depends on the distance r only. Okay. So one more example we have to consider, and then we have to stop. So this is the last article. So pay attention, less than a 1 minute article is pending. If we able to finish this, it's okay. So this is 120 joule of work is done, carrying a charge 6 coulomb from a place where potential is 10 volt to another place. Means one place whose potential is 10, another place we don't know the potential, and that potential we have to find out. Okay. So we consider here, so that potential is V. So work done 120, charge 6 coulomb, potential at one point A is 10 volt, potential at B is V. So potential difference formula is the point C. Potential energy of single charge in external field. This word is very important. Potential energy of charge Q at a point in external electric field of intensity E. Electric intensity is E. Okay? Charge is Q, E is electric intensity. Work done by external agency to bring charge Q from infinity to that point without change in kinetic energy. And that work done is potential energy, and it is given by this formula. Charge multiplied by potential. So when we are considering external field, then potential energy is given by this formula. We have to find out potential multiplied by charge. So VR is the potential at that distance R, and Q is the charge. So when potential energy of the single charge in external field we are considering, we have to use this one. Potential energy of system of two charges in an external field. Now here, two charge in external field. Consider positions A and B. Now I have to consider two positions. We consider two positions A and B in given electric field whose potential is V1 and V2. They are the two potentials at point A and B respectively. Work done to bring a charge Q1 at A is given by this formula. This is the first work done. Similar manner, work done to bring Q2 at point B. A charge Q2 at point B, it is given by formula. W2 is equal to, you can see here, W2 is equal to this. Take it. Now pay attention here. But here, when we are considering work done to bring a charge Q2 at point B, that time at point A the charge Q1 is already present. So the work done is given by formula. The work done to bring a charge Q2 at point B is sum of work done against the external field and work done against the field of Q1. Means against the external field and against the field of Q1, we have to do the work done. So this work done is given by this formula. Okay. So it is Q2 into V2 plus 1 upon 4 pi epsilon 0 Q1 Q2 divided by R12. Or you can write net work done is given by this formula. Total work done to bring A and B at a point in electric field A and B. So it is Q1 V1. It is the work done to bring a charge 1 Q1 from infinity to point A. Okay? And this is work done to bring a charge Q2 from infinity to point B. Okay? If pay attention, this is only work done in absence of external field. But if the external field is there, we have to consider that work also. So we have to add this. Okay? So why we add this? Because here the external field is there. And then potential energy is given by this formula. You can see this formula. So when the problems are asked, you have to remember this. So previous to means single charge system and multiple charge system, we consider external field is absent. But here when we consider the external field, that time we have to consider that part also, and that we have to add in the net work done. I hope you understood this. Problem: two charged particles having equal charge, 3 into 10 raised to minus 5 Coulomb. Each are brought from infinity. They are brought from infinity to a separation 30 centimeter. They are brought from infinity to a point having a separation 30 centimeter. Find increase in electrostatic potential energy during the process. Find increase in electrostatic potential energy during the process. Now, taking potential energy at infinity to be 0, means at infinity potential energy is 0. So increase in potential energy is equal to present potential energy, because potential energy at infinity is 0, that you remember. So we can write formula of the potential energy. V is equal to Q1 Q2 divided by 4 pi epsilon 0 R. Now Q1 and Q2 both are same. So 3 into 10 raised to minus 5 bracket square. And 1 upon 4 pi epsilon 0 having this value. And divided by the separation is 30 centimeter, means 0.3 meter. Okay, after solving this, we get 27 joule is the potential energy. Listen, you remember when we are solving the MCQs also based on the potential energy, these examples are helpful. Now next one. Determine the electrostatic potential energy of a system consisting of two charges, minus 2 microcoulomb and plus 4 microcoulomb, with no external field. Okay? No external field. Placed at minus 8 centimeter, minus 8, 0, 0, and plus 8 centimeter, 0, 0. These are the two coordinates are given for these two charges. Okay. B part. Suppose same system of charges. Now place in external field. Now pay attention. Same question. Only the thing is external field is present. So initially in part A, no external field. Now the second part, external field is there. Now how to solve? See here, you know the given charge 1, okay, that we converted into the Coulomb. Distance 1, ठीक है, 0.08 centimeter. Charge to 4 microcoulomb. We converted into the coulomb. Distance is 0.08 centimeter. ठीक है. Now, pay attention. This is R1 and this is R2. One is plus and one is minus. ठीक है. So R we can write. So R we can write R1 minus R2. So R1 is 8 minus minus plus 8. It is coming 16. Okay? So it is written 16 centimeter, that you remember. So electrostatic potential energy of two charge system. For two charge system, you know that this is the formula. Q1, Q2 and distance we substitute and we get this answer. So this is the electrostatic potential. Now, external field is present. That time we have to consider work done by these charges against the external field also. Okay? So this is a formula. Just we learn how we obtain. So this is the work done to bring a charge Q1. This is work done to bring a charge Q2. Okay? And this is the work done by the field. This is the potential energy. Now, you know that electric intensity is given by this formula. Potential is given by this formula. E into dr. Or you know that this same formula we can write like this way also. Because this V is equal to A by R. V is A by R. You know the formula of E. E is equal to V by R or dV by dr. Okay? And if you substitute V is A by R, we get this formula for electric intensity. Okay? Now total potential energy is, so this formula we are written as it is here. Okay? So this we are written. So this is the potential. By using this we are written potential is A by R. Okay? Potential is A by R. Into this Q1. So A by R1 into Q1. A by R2 into this Q2. So this formula we are written. Now we have to substitute the values. Now pay attention here. So this is coming 0.45. So that we solved in the previous part. Then Q1 minus 2 into 10 raised to minus 6. So distance is this. We are taken magnitude. So distance R2 is also we are taken in magnitude 0.08. This electric intensity, you know that it is equal to A divided by R square. Okay? By using that we can find out A, which is 8 into 10 raised to 5, which is given here. You can see this is A. So we substitute A. This is Q1. Here again A. This is Q2 and this is R2. We solve this, then we get potential energy. So this is the expression for potential energy. Now listen, you remember these formulas for problem only. If the problem is asked, you must have idea how to deal with such type of problems about the potential energy. Dear student, in today's lecture, we have to start equipotential surfaces. So name suggests everything about it. Equipotential. Equipotential means equal potential surfaces. Whose potential is equal, these surfaces are called as equipotential surfaces. So you can see here, the surface over which the electric potential is same at all points. is called as equipotential surfaces. And if the potential is same at all points, then it is called as equipotential surface. Now we consider here this is a uniform electric field. So this is a uniform electric field. So this is the direction of the electric field, you can see. So these surfaces, so this is first surface, second surface, third surface. These three surfaces are called as equipotential surfaces. Okay. At every point of this surface, electric intensity is same, electric potential is same, so they are called as equal potential surfaces. So potential, if I consider here it is V1, here it is V2, here V3. Then we can write these are the planes of equipotential surfaces. Now for isolated charge, means pay attention. So this in uniform electric field, this is the first equipotential surface, second equipotential surface, third equipotential surface. Now I consider isolated charge here. You can see it is represented by plus. Then this is the direction of electric intensity. We know that electric intensity is directed away from positive charge. So this is the direction of electric intensity. Now we have to show equipotential surfaces here. Now if I draw, so this is circle, you can see this circle. So this is equipotential surface. At all point of this first circle, the potential is same. So this is equipotential surface. Now second surface. So this is second equipotential surface. At all point potential is same. This is third equipotential surface. And the next one is the fourth. So they are the equipotential surfaces for isolated charge. So here we shown first, second, third, and this is the fourth. 4 equipotential surfaces. You remember the potential of all the 4 surfaces are different. Huh? So here in this diagram, this V1, V2, V3, they are not same. They are not same, that you remember. Again, but all the point of these surfaces having equal potential. So this is the equipotential. Similar manner here. So this is the first circle, second circle, third, fourth. At all point, the potential is same. So they are the equipotential surfaces. Or you can say a sphere. If you draw a sphere around this charge, at every portion of this sphere, potential is same. So this is the equipotential surface. Okay. Now everybody know the formula of the potential. This is the formula of potential. V is equal to 1 upon 4 pi epsilon 0 Q by R. So this is the formula of potential. Now here after that, we have to learn some properties of equipotential surfaces. Properties. The first property is no work is done. See this, very important. No work is done in moving a test charge from one point to another point on equipotential surface. Just we in the previous class we learned one formula of potential difference. VA minus VB is equal to work done to displace a charge between point A to B divided by a charge. So this is the formula for potential difference. Now let I write the formula of work done. VA minus VB into this charge. If potential is equal, equipotential. Equipotential surfaces means here VA and VB both are same. Both the potential are same. If we substitute VA and VB same, then subtraction VA minus VB is coming 0. 0 into this Q is 0. So work done to displace a charge between 2 points or 2 points of equipotential surfaces is 0 or no work done. Okay. So this is the formula. By that we already learn how we get the work done, 0. So here again everything is explained. Up to that, second property. The electric field is always perpendicular to the element of this dl of the equipotential surface. And this dl is a length element basically. Okay? So electric field is always perpendicular to the equipotential surfaces. Just we learn some concentric spheres, concentric circles. Okay? In that we shown direction of electric field. This is the direction of E. Now in this direction, this is the electric intensity. Now here this electric intensity and equipotential surface, you can see it is perpendicular to the length element of equipotential surface. This is the length element. This is dl. Now since no work is done on equipotential surface, so work done is 0. So we can write here E dl cos theta is 0 by this formula. Now third property. Equipotential surfaces indicate region of strong or weak electric field. Electric field is defined as negative potential gradient. We learn E is equal to minus dV by dx. So E is equal to minus of dV by dx is potential gradient. So electric intensity is, by this formula, electric intensity is negative potential gradient. Hence, this dx is equal to minus dV by E also we write. This dV, potential is constant because it's an equipotential surface. So we can write, if this dV is constant, then dx and E, they are inversely related. This distance and this electric intensity, they are inversely related. What exactly it indicates that? Just let I explain with some simple diagram. If I consider this is the first surface, just a bit. This is the first. This is equipotential surface. Now I consider one more equipotential surface here. Now I consider one more equipotential surface. Okay. So this is the charge and this is direction of electric intensity. Equipotential surfaces indicate region of strong or weak electric field. So electric field at this point means electric intensity at this point and at this point. It is different. Okay? And it is related with the distance by this formula. So as distance increases, electric intensity decreases. Now the fourth property. Two equipotential surfaces cannot intersect. Two equal potential surfaces cannot intersect each other. That you remember. And if two equipotential surfaces intersect, then the potential of the intersection, there will be two values of the electric potential. If the two equipotential surfaces intersect, then two values of the electric potential, and which is not possible. Therefore, two equipotential surfaces cannot intersect. Now next one. So here some point to remember. Electric potential is a scalar quantity, whereas potential gradient is a vector quantity. So generally, this electric potential V scalar, then E, it is vector, as well as you know that potential gradient dV by dx is vector, is a vector quantity. And this negative sign, you know that E is equal to minus dV by dx. The negative sign of potential gradient shows that the rate of change of potential with distance is always against the electric intensity. So this rate of change of potential with distance is against the electric intensity. And because of that, a negative sign we write here. Now one problem we have to learn. Two particles carrying an electronic charge is suspended in equilibrium between two horizontal metal plates separated by 10 centimeter and having a potential difference 4000 volt. Calculate mass of the oil drop. You remember one thing here. This is very important. Equilibrium. A particle carrying a charge, particle having some charge, and it is suspended between two metal plates. Okay? A charge is between two metal plates and it is in equilibrium. And these are the two plates and this is a charge. It is in equilibrium, not going down, not going up. So here, this is the answer. So here, the charge is given. It's an electron. So electron means charge is 1.6 into 10 raised to minus 19 Coulomb. So potential 4000 volt separated by 10 centimeter distance between two plates. 10 centimeter, we can write it as a 0.1 meter or 10 into 10 raised to minus 2 also you can write. Calculate mass. So pay attention here, the charge is in equilibrium. So force, why it is in equilibrium? Pay attention, the charge is not going down as well as not going up. So it means that some force balances this. So this force due to electric field balances the weight. So force due to electric field balances, pay attention here, the metal plates are horizontal. This is the first plate. Sorry, I shown here vertical. This is the first plate, this is second plate. First, second plate, and this is a charge. Now, obviously, the weight is acting on charge in downward direction mg. And in upward direction, some force due to electric field or electrostatic, means this force due to this electric field is applied. And it is in equilibrium, means not moving up and not moving down. So these two forces balances each other. So we are written force due to electric field. So we know the formula of electric intensity, it is F by Q. So by this formula, force is coming QE. By the formula of electric intensity, we get force is equal to QE. And weight, everybody know that weight is mg. So weight is mg. Okay? So we have written this formula. So mass we get QE divided by g. So charge is given, but E, electric field intensity, is not given. But instead of that, they given potential. So we can use this formula, E is equal to dV by dx, and we find out electric intensity, which is 4 into 10 raised to 4. Then we substitute that electric intensity. G we have taken 9.8. So this is E, this is charge, and after solving we get this is the mass. So mass is 6.53 into 10 raised to minus 16 kg. When the problems are asked, you have to remember how to solve these problems. Now, next article is electrostatic potential energy. The work done in moving a charge Q. Work done moving a charge Q from infinity to a point in the field against the electric force is electrostatic potential energy. In the previous article also we learned the work done to move a charge, unit positive charge we can say, or charge Q, from infinity to point in electric field is called as electrostatic potential energy. So work done is given by this formula. Electrostatic potential energy of two charge system. Now let me discuss electrostatic potential energy of two charge system. Then we discuss three charge system, multiple charge system. So first we have to consider this. To find potential energy of two charge system, we consider first charge Q1, second charge Q2 are initially at infinity. They are initially at infinity. Q1, first Q1 is brought from infinity to point A. The charge Q1 we brought from infinity to point A. As there is no field, no work done. Now charge Q2 is brought from infinity to point B. Now here simply both the charges Q1 and Q2 we brought from infinity to point A and B respectively. As charge Q1 repel Q2 because no field initially as at these 2 points. Now the Q1 and Q2 they start repelling each other. Work is done in the process when one charge exerts some force on another charge. Okay? Some work is done. You can see these two charges in a diagram. This is charge Q1 and charge Q2. We brought these two charges from infinity to point A and infinity to point B. Then I consider this is the origin. Distance of charge Q1 is R1 or position vector. We can say that R1 bar represent position vector. R2 bar represent position vector for the second charge Q2. They are the position vectors. By trigonometry, or you can say that you know that laws of vector. By laws of vector, triangle law of vector addition. So this we get R2 bar minus R1 bar. You know the triangle law of vector addition. If this is the first vector, this is second vector, ठीक है. Then addition of these two is third vector. ठीक है. That everybody know. So we use that, and by using that we get a formula. Now, electrostatic potential energy for these two charge system is given by this formula. 1 upon 4 pi epsilon 0, first charge multiplied by second charge divided by this distance between two charges, R2 bar minus R1 bar. So this is electrostatic potential energy for two charge system. Now we can consider the more than two charges also. You remember, we have to solve a problems in that maybe two charges are given, then what to use to find out electrostatic potential energy. More than two charges, then what we have to use, that we have to learn here. The same formula in magnitude wise we can write like this. So this is the magnitude, 1 upon 4 pi epsilon 0 q1 q2 divided by r12. R12 means what? Distance between charge 1 and 2. R12 represent distance between charge 1 and 2. Now, three charge system. Electrostatic potential energy of three charge system. Three charges system. So again, charge 1 which is at A, charge 2 which is at B, one more charge we consider Q3 which is at point C. Now we consider their distance from the origin. So these are the position vectors. Position vector for charge 1 is R1 bar, second R2 bar, and third R3 bar. You can see in a diagram. Now distance between the charges we can consider. Distance between charge 1 and 3, then 1 and 2. Okay, this is, we can write this is distance 1, 3. This is distance 1, 2. Distance between charge 1 and 2. Then distance between charge 2 and 3. R2, 3. These are the distances. Okay. Or we can write it in vector form also. You remember in this format, or you can remember in vector format. Okay. So this is the distance between, means this is the R3 minus R1 bar. So this is R3 bar minus R1 bar. It is the distance between these two. Okay. R3 is the larger, R1 is the smaller. Similar manner. So this is R3 minus R2. And this is R2 bar minus R1 bar, which is similar to the previous one. Now, we have to find out electrostatic potential energy for this three charge system. So this is the formula for electrostatic potential energy. This is the formula for electrostatic potential energy. So electrostatic potential energy U is equal to U between 1 and 2, 1 and 3, and 2 and 3. You can see here charge 1 and 2, 1, 2, then here 1, 3, okay, and 2, 3. We are not repeated any combination 1, 2, 1, 3, 2, 3. No repetition in the combination here. Now, electrostatic potential energy formula we know. By that formula we can write. So this is the expression for electrostatic potential energy. Or in another word, we can write like this in magnitude wise, 1 upon 4 pi epsilon 0. So charge 1 and 2 first. Okay, here it's a electrostatic potential energy between 1 and 2. Then 1 and 3. And then 2 and 3. So you can see here the distances. So 1 and 2, between charge 3 and 1, it is a distance 3 and 2. Or you can write like this here also, between 2 and 3. So both having a same meaning. Or we can write like this also. Anyways, you can remember for problem solving. Now, after that, n charges. We are considering system of n charges. We consider 2 charges, then 3 charges, now n charges system. The formula is, this is the formula. Or we can write, here you can see this formula. So this is 1 upon 4 pi epsilon 0, summation sign qi into qj. Okay, divided by rj minus ri. So this is for all pairs. So we have to see one problem based on this. Let's see the problem. So the concept is clear. So this is the problem related to potential energy. 2 charges of magnitude phi nanocoulomb and minus 2 nanocoulomb are placed at a point. You can see the positions of these charges. So x, y, z coordinates are given. In a region of space where there is no other external field. No other field. Find electrostatic potential energy of the system. So first charge Q1, it is in nanocoulomb. Nano means 10 raised to minus 9. So we are converted into the coulomb. Again, second charge in nanocoulomb, we converted into the coulomb by multiplying 10 raised to minus 9. Now, electrostatic potential energy. This is the formula. These are the 2 charges system. So this is the formula. So 1 upon 4 pi epsilon 0 is 9 into 10 raised to 9. This is Q1, this is Q2, and this is the distance. Why this is the distance? Because you can see here, this is a 0 coordinate, this is 0 coordinate, 0 coordinate. Okay? So 20 minus 2 is coming 18. This is a R. We already learned how to find out a potential energy between 2 charge system. So if instead of 0, any other number is written, then the formula is different. So that distance also we have to consider. Now after solving this, we get this is a potential energy. Minus 5 into 10 raised to minus 7 joule. Or if you want to write it in microjoule, then we can write like this. 0.5 microjoule. So this is for 2 charge system. Now we consider one more example where more than 2 charges are there. So this is second example. Calculate electrostatic potential energy of system of charges shown in figure. How many charges are there? So this is a plus Q charge, plus Q, first charge, second charge, third charge, fourth charge. Okay, this is a general formula. Okay. So potential energy, electrostatic potential energy is given by this formula. So it is 1 upon 4 pi epsilon 0 is common everywhere. Then Q into Q, this charge multiplied by this. Okay. So we are written Q multiplied by Q. Both are positive, you can see here. And distance between these two is R. Okay. Now, This is the first charge and this is second minus charge. Okay, this is first and this is then next charge. It is a minus q charge. Again, distance is r. This is all sides are same. Okay, you can see here the distance is r. Now we consider this. Let I name the charge 1, 2, 3, and 4. Here we consider the first one between 1 and 2. Now here 1 and 4. Now 1 and 3. Now by Pythagoras you can find out this distance. If this is r, then you can find out this distance is r square plus r square. 2r square means what? 2r square we get this hypotenuse square. So root 2r is this distance. So this distance is root 2r. So 1 and 3 means this q and minus q. You can see here between 1 and 3 distance is r root 2. So means 1, we consider 1 and 2, 1 and 3, 1 and 4. You can see here 1 and 2, then this is 1 and 4, 1 and 3. Now next combination we can consider 2 and 3. Okay, between this 2 and 3. So 2 means plus q into minus q. You can see here this is a plus q and this is a minus q. And distance is, you can see here, distance is r. Distance is r. Now 2 and 4 we have to consider. Now this 2 and 4. Then this plus q and minus q. So you can see here plus q minus q. And distance is again this. By Pythagoras you get it is again root 2r. Okay, this combination is also over. Means we consider 2, 3, 2, 4. Okay, now we consider, we cannot consider 2 and 1. Huh? You remember 2 and 1 we already written here. 2 and 1 and 2 both are same. Huh? Okay, so we consider 2, 3, 2, 4. Now 3, 4. So this combination. You can see 3 is minus q multiplied by minus q. You can see here minus q multiplied by minus q. Divide by r. So this is the formula we get. Now we can substitute here. Q into q, q square. This minus q into plus q, minus q square you can see. This is minus q multiplied by minus q plus q square. Then again here minus q square. Here minus q square. Here minus q square. Divided by the corresponding distances. After solving this, we get this is the answer. So just I explained here how to find out potential energy of a multiple charge system. If it is a 2 charge system and a more than 2 charge system, how to find out potential energy, that I explained here. Now, potential energy of single charge in external field. When we are considering in this lecture, we have to start article potential energy of a dipole in an external field. Dipole means it's an electric dipole. Electric dipole means two equal and opposite charges separated by finite distance is called as electric dipole. Now here we consider a electric dipole. We consider electric dipole. So two charges we consider plus q and minus q separated by finite distance 2l. The 2l in uniform electric field of intensity E. So this is the diagram. So you can see in a diagram two charges. This is plus Q charge, this is minus Q charge. They are separated by some finite distance 2L. And this is the electric intensity, electric field intensity. So this dipole making some angle theta with the direction of electric intensity. So this is theta. Then due to this electric field, some force is experienced by both the charges. The force experienced by charge plus Q. Force experienced by this charge plus Q is QE. How we get this formula? We know that electric intensity is given by formula F by Q. So by that formula, F is equal to QE. This is the formula. So force acting on this plus Q charge is QE. Similarly, force acting on this minus Q is minus QE. Minus QE is the force. This dipole experiences a torque. Dipole experiences a torque. And because of this torque, it rotates. You can see here. So this is the force on charge plus Q, and this is the force on charge minus Q. Both the forces are equal and opposite. Equal and opposite forces are there. So equal and opposite forces are there. So dipole experiences torque. So it tends to rotate. So we can write the formula of torque. So torque is given by formula P bar cross E bar. So P bar cross E bar is torque. So that formula we can write PE sine theta also. So this formula we can write in magnitude PE sine theta. So this is the torque. This is torque acting on dipole. If we consider this dipole rotate from theta 0 to theta. If the dipole rotate from angle theta 0 to theta, then work done by external torque is given by. Now we have to write formula of work done. So work done is given by this formula. You can see here work done is given by integration of this torque multiplied by d theta. External torque multiplied by d theta within the limit theta 0 to theta. Because we have to, this dipole is rotated with some angle from theta 0 to theta. So you know that work done in translational motion is force into displacement. So it's a rotational motion. So torque into this angular displacement. This is the work done. So total work done is given by the integration of this. Now we substitute the value of this torque. We substitute torque. So torque is PE sine theta and this is d theta as it is. Now P is electric dipole moment, E is electric intensity, both are constant, take it outside. So integration of sine theta d theta only. So PE we are taken outside, so integration of sine theta d theta. Integration is applicable to this term only. So integration of sine theta d theta is minus cos theta. Integration of sine theta d theta is minus cos theta within the limit theta 0 to theta. So that limit we are written at the end. Now we have to substitute upper and lower limit. So this PE as it is, instead of this theta we write this upper limit theta. So minus cos theta, then minus sine, and then instead of theta we have to write lower limit. This minus sine and this minus cos theta 0. This minus minus is plus. You can see here this minus and minus get converted into a plus sign. So in next step we can write the plus sign. You can see here. Okay. So in a bracket we get work done is equal to PE in a bracket minus cos theta plus cos theta 0. Or we can write this minus cos theta later and this cos theta 0 first. So we get the next step. Work done is equal to PE in a bracket cos theta 0 minus cos theta. ये जो माइनस है हमने बाद में लिखा है, ये फर्स्ट लिखा है. Now you remember this work done stored as a potential energy. The work done is stored as electrostatic potential energy of the system in the position when dipole makes an angle theta. When the dipole making an angle theta with electric field. Now, the zero potential energy can be chosen as per convenience. We have to choose a zero potential energy point. Now, zero potential energy, we can consider the initial position. Initially, so this initial potential energy we consider zero. So here, as per our convenience, we consider zero potential energy point only. So this potential energy when the angle is theta 0 is 0. Means initial potential energy is 0. So that we have to substitute. We get potential energy is equal to. So potential energy we can write this is the potential energy, and this potential energy we have chosen 0. Okay, it is 0 that we selected. So potential energy is equal to, we can write potential energy is equal to PE in a bracket cos theta 0 minus cos theta. So this is the potential energy. Okay, so we have written formula of potential energy. PE in a bracket cos theta 0 minus cos theta. Because we chosen here a one, means as per our convenience we consider the zero potential energy point. Okay, so we get potential energy formula PE in a bracket cos theta 0 minus cos theta. When the dipole is rotated with angle theta 0 to theta, then this is the potential energy. Now, so this is the formula of the potential energy. We have to learn some cases. Some cases we have to consider here. The first case, if initially the dipole is perpendicular to electric field. If the dipole is perpendicular to the electric field, then this theta is 90 degree. That we substitute, means this initial angle, theta 0 is 90 degree. Then potential energy we get PE in a bracket cos theta 0 means cos 90 minus cos theta. You know that cos 90 is 0. So this term get cancelled. So PE in a bracket 0 minus cos theta. 0 minus cos theta means minus cos theta. So we get a potential energy minus PE into cos theta. So this is potential energy when dipole is perpendicular. When dipole is perpendicular to the electric field. The same formula we can write like this way also. Minus sign P bar dot E bar. You know that P bar dot E bar is PE cos theta. Okay, and this minus sign has it. So this is the formula for potential energy when dipole is perpendicular to the electric field. Now when it is parallel, if initially the dipole is parallel to the electric field, means initial angle theta 0 is 0. Okay? If it is 0, then we can write potential energy is PE cos 0 minus cos theta. This cos 0 is coming 1. So it is PE 1 minus cos theta is the potential energy formula. So potential energy we get PE in a bracket 1 minus cos theta. Now we see one problem based on this article. So the concept is more clear. Now, so electric dipole. An electric dipole consists of two opposite charges. Two opposite charges, each of magnitude 1 microcoulomb. Means one is first charge is plus 1 microcoulomb and second is minus 1 microcoulomb. Separated by 2 centimeter. Means this is a distance between two charges. You know that distance between two charges is, if this is the first charge, this is second charge. Okay, plus Q minus Q. The distance between two charges is represented by 2L. This is 2L. The dipole is placed in external electric field. This is the external electric field. 10 raised to 5 Newton per Coulomb. So this is the external electric field. And we have to find out, you can see the first point. The first point is maximum torque exerted by field on the dipole. So we have to find out maximum torque. Okay. So let me find out first maximum torque. The maximum torque we can find out by this formula. Maximum torque when the angle is this 90. Okay. So we get formula PE sin theta. So P is, now P is given by formula. You know the P electric dipole moment, Q multiplied by 2L. So charge is 1 microcoulomb means 1 into 10 raised to minus 6. This is Q. And 2L. So it is 2 centimeter. 2 centimeter means 2 into 10 raised to minus 2. This is 2L. So after substituting, we get electric dipole moment is 2 into 10 raised to minus 8 centimeter. Coulomb centimeter. Sorry, Coulomb meter. So it's not centimeter, it's a capital C. Coulomb meter. Now electric intensity is 10 raised to 5 Newton per Coulomb. We can substitute dipole moment, electric intensity, and sin 90 is 1. So we get maximum torque is 2 into 10 raised to minus 3 Newton meter. 2 into 10 raised to minus 3 Newton meter is the maximum torque. Now, second point, work done or the work the external agent will have to do in turning the dipole through 180 degree starting from the position 0 degree, means 0 degree to 180 degree. Okay, that work done we have to find out. So that work done is PE cos theta 1 minus cos theta 2, or you can write like this way also. So this W is equal to PE in a bracket cos theta 0 minus cos theta. So theta 0 is 0 degree and theta is 180 degree. You can write in any way. Then P is 2 into 10 raised to minus 8 multiplied by E is 10 raised to 5 cos 0 minus cos 180. Cos 180 is how much? Cos 180 is minus 1 and cos 0 degree is 1. So 1 minus minus 1. So 1 plus 1. So we get 2 into 10 raised to minus 3 into 2. 1 plus 1 is 2. So 2 into 2, 4. So we get answer 4 into 10 raised to minus 3 joule. And this is work done to rotate a dipole from 0 degree to 180 degree. I hope you understood this concept. Listen, so I repeat this. Conductors and insulator we have to learn. Conductors are the material which contain large number of free electrons and allow flow of charges. Insulator do not have free electron. Means insulator bad conductor of electricity, that you know that. Now here, electrostatics of conductor. Inside conductor, the electrostatic field is zero. You note down this point. Inside conductor, electrostatic field is zero. So related to that, I will tell you one article we learn. If this is a charged conductor, okay, these are the positive charges given to this conductor. Now inside this conductor, electric intensity is zero. So that is the point number one. Inside conductor, electrostatic field is zero. And the electric intensity is zero. Second, potential is constant. Means V is constant for inside point. Okay? Potential is constant within and on the surface of conductor. So within and on the surface of conductor, the potential is constant. Third point, the interior of the conductor has no excess charge in static equilibrium. Interior of the conductor has no excess charge in static equilibrium. Interior means inside portion, no excess charge. Next point, the electric field just outside charged conductor is directed perpendicular to the surface of conductor at every point. So if you want to consider electric field at this point or on the surface of the conductor, so that electric intensity is perpendicular to this. This angle is 90 degree. Angle is 90 degree. Next one, surface charge density of conductor could be different at different point. Surface charge density means charge per unit area. Sigma, charge per unit area. It is different at different point. So these are the some points which we have to consider in the next articles. So this is a basic. You already covered these articles previously also. So it's a just kind of revision. It's a revision. Now, so here what is dielectrics and polarization? That is the next and important article. So let I tell you in short what is dielectric first. So dielectric are insulators. Note this word. Dielectric are insulators. And you know that insulator means do not have free electron. So dielectric are insulator which do not permit passage of charges through them. Now, this dielectric are classified into two categories. This dielectric is classified into two categories. And these two categories we have to learn. So dielectric is classified into two types. First one is polar dielectric material or polar molecule. Or you can write the heading polar dielectric. And second one is non-polar. Now what is polar dielectric and what is non-polar dielectric? So this is very important concept in next article point of view. Polar means a molecule in which the center of positive charges does not coincide. So this word is very important. Does not coincide with the center of negative charges. With the center of negative charges. Means center of positive charges and negative charges in a molecule. They are not coinciding. If they are not coincide, means the molecule is polar molecule. The molecule is polar molecule. Now we consider one example. So this is H2O molecule. Now, in simple word, what is the center of positive charge? You know that the structure of atom. So central part is the nucleus. Inside the nucleus, all the protons are there. They're having a positive charge. So this hydrogen atom also having a positive charges. This also having a positive charges, and this hydrogen also having a positive charges. Then center of these positive charges may be here at this point. This is the center of positive charges. Maybe at any point. Similar manner, every atom having electrons, means oxygen and this hydrogen atom having electrons, they are revolving around the nucleus. The center of that negative charges, all the negative charges may be at different point at this point. And if these two centers are not coinciding, then that molecule is called as polar dielectric molecule or polar dielectric. I hope you understood the polar. Polar means the center of positive and negative charges does not coincide. So this word is very important, does not coincide. So non-polar means opposite to that where they coincide. Polar means does not coincide and non-polar means coincide. Now you can see here the H2O molecule. The structure is like this. So dipole moment of this molecule is shown like this. So polar molecule does not have symmetrical shape. So when we are talking about the polar molecule, their shape is not symmetric. And because of that, their centers of positive and negative charges are not coinciding. Examples: HCl, H2O, NH3, CO2, alcohol, etc. Many examples we can write, but few examples we consider. Now, we have to learn effect of electric field on polar molecule. Now, when we are talking about the polar molecule, when we place polar molecules in electric field, then what happens? That we have to learn. So this is the polar molecules or polar dielectric. Okay, this is polar dielectric. It is in the absence of electric field. You can see here electric field is 0. Electric field is 0. We have to learn effect of electric field. अगर हम इलेक्ट्रिक फील्ड अप्लाई करते हैं तो ये जो पोलर मॉलिक्यूल्स है उसके ऊपर क्या इफेक्ट होता है, दैट इफेक्ट वी हैव टू लर्न. ठीक है. सो हियर दिस डाइपोल मोमेंट्स आर अरेंज्ड रैंडमली. So when we are talking about individual molecule, it has a dipole moment. But when we consider a set of molecules, then their dipole moments are aligned randomly. You can see here. So for this molecule, dipole moment is in this direction. Okay? This molecule, dipole moment is in this direction. So here the dipole moment is in this direction. You can see the direction. So here dipole moment is in this direction. So dipole moment of every polar molecule is aligned randomly. Okay, it is randomly. Okay. So in absence of external electric field, the permanent dipoles, means this dipole basically, of the molecules orient random. They are oriented random. Hence, net dipole moment is zero. So dipole moment of one molecule cancel with another. So total dipole moment is zero. You can see here, we are written here. So dipole moment is zero. Now, when we apply electric field, now this is the case one where the electric field is zero. Now we have to apply some electric field. You can see when we apply some electric field. Pay attention. Now this is the polar molecules. When we apply electric field, you can see the change. You can see the change. So this is in absence of electric field initially. You can see this is in absence of electric field. So both the diagrams are similar. But as we apply electric field, then so their dipole moments are oriented in the direction of electric field. So this is the direction of electric field. You can see here most of the molecule align their dipole moment in the direction of electric field. So you can see here dipole moment align in the oriented in the direction of electric field. So here these molecules having some dipole moment. Here dipole moment is zero. So here dipole moment is zero. But here it has some dipole moment and it is in this direction. Because these dipole means polar molecule oriented themselves in the direction of electric field. So you can see here. Hence dipole moment is induced. Here some dipole moment is produced. Pay attention. When electric field is zero, dipole moment is zero. When we apply some electric field, then it has resultant dipole moment because the polar molecule orient themselves in the direction, their dipole in the direction of electric field. So this is the polar molecule. Similar manner we have to learn non-polar molecule. Non-polar molecules. Now next we have to learn non-polar molecules or non-polar dielectric. Non-polar dielectric. So non-polar means centers of positive charge and negative charge coincide. So you can see here the word coincide. A molecule in which centers of positive charges coincide with the center of negative charges is called as non-polar. Non-polar molecule has symmetrical shape. Their shape is symmetrical, and because of that symmetrical shape, the centers of positive and negative charges coincide with each other. Examples: N2, CH4, O2, C6, H6, etc. These are the examples. Now, we have to learn effect of electric field on non-polar molecules. So you can see a diagram. So this is the diagram in absence of electric field. So when electric field is zero, maybe here the centers of negative and positive charges coincide. So they coincide here. Okay? positive and negative charges centers are coinciding. So dipole is not produced here. So when the dipole is produced, when positive charge and negative charge centers are at different points. In this means here dipole is not produced. So dipole moment is 0 here. You can see here dipole moment is 0. Because positive charge and negative charge is at same point, or you can see, so dipole moment is q into 2l. So 2l is the distance between two charges. But here both the positive charge center and negative charge center is at same point, so dipole moment is 0 here. So you can see here, in absence of external electric field, effective position and negative centers coincide. Effective positive and negative center coincide. Hence, dipole is not formed. So, if the dipole is not formed, means no dipole moment. You can see dipole moment 0. Now, we have to see when we apply electric field what happens. Now, this is the diagram. In absence of electric field. But when we apply electric field, you can see the change. I repeat this diagram again. In absence of electric field, this is the diagram. When we apply electric field, you can see the change. Then centers of positive and negative charge, they are not coincide to each other. So dipole is produced here. Some dipole moment is there, and that dipole moment is in the direction of electric field. When electric field is applied, positive charge and positive charges are pushed in the direction of electric field. Positive charges are pushed in the direction of electric field, and negative charges opposite to the direction of electric field. Means positive charges are pushed in this direction and negative charges in this direction. Due to separation of this positive charge and negative charge centers, some dipole is formed. Dipole moment is there. Here we get the dipole because positive charges are pushed in the direction of electric field and negative opposite to that. So dipole is formed here. Now what is dielectrics? Generally, a non-conducting medium or insulator is called as dielectric. Precisely, non-conducting material in which induced charges are produced on their faces on the application of electric field are called as dielectric. Example: air, H2, glass, mica, paraffin, wax, etc. These are the example of dielectric. Polarization of dielectric. Now, what is polarization of dielectric? So, when non-polar dielectrics act, so you note this word, when non-polar dielectric slab is subjected to electric field, dipole are induced due to separation of positive and negative centers. So this is a positively charged plate, this is negatively charged plate. In between this dielectric material is there, and it is a non-polar dielectric. Here we highlighted this word, non-polar. And when we apply the electric field E0 to this dielectric slab, then so here some dipole are induced, and because of that some electric field is created, and it is EP. EP is the electric field due to this dielectric. So E0, you can see here, E0 is the applied field, EP is the induced field. induced field due to this dipole. So resultant electric field is, you can see here, resultant electric field is E0 minus EP, because resultant electric field is vector addition of these two, and these two having opposite direction. So E0 minus EP is the resultant electric field. Dielectric constant. By using this, we can find out dielectric constant given for this dielectric slab is given by this formula. E0 divided by E0 minus EP. This is the formula for dielectric constant that you remember. Dielectric constant E0 upon E0 minus EP. E0 is applied electric field, and E0 minus EP is the resultant electric field or net electric field. So this is the formula for the dielectric. After this, polarization vector. What is polarization vector? Polarization basically measures the degree of polarization of dielectric. It measures the degree of polarization of dielectric, and it is defined as dipole moment of unit volume of polarized dielectric, or dipole moment per unit volume. Electric dipole moment per unit volume is the polarization. Or we can write this polarization in terms of susceptibility. So here you can see P for polarization. Xe is electric susceptibility. E is electric field intensity. So where X is the constant, and this constant is called as electric susceptibility. Electric susceptibility is a constant for that electric medium that you remember. And in this formula E is the electric intensity. Now dielectric constant of various material we discuss, the values we consider here. You can see here dielectric constant for a certain material when we are talking about this air. So for air, dielectric constant is minimum and maximum, you can see. Okay, it is for air, dielectric constant is 1. For other medium, dielectric constant having a different value, but these values is greater than 1. And for metal, you can see here dielectric constant is, for metal it is infinity. Means here you remember dielectric constant K is equal to 1 for air, but other medium, for other medium dielectric constant is always greater than 1. For other medium it is 1. Okay? And for air it is 1. For air or vacuum it is 1, and other medium it is greater than 1. And for metal it is infinity. Now new article we have to start, and it is capacitors. So what is capacitors? Capacitor is a device generally used for storing electric charge. Capacitor is a device for storing electric charge. The measure of ability of conductor to store charge in is known as capacitance or capacity. The ability of conductor to store charges is known as capacitance or capacity. Ability, every conductor having its own ability to store charges, and it is capacitance or capacity. Now you know that when we are considering about an uncharged conductor, As we start increasing charges on the conductor, then its potential also start increasing. So as charge increases, potential increases. So we can write Q proportional to V. As charge increases, potential increases. Hence, we can write the same equation by writing constant. So Q is equal to CV, and where C is a constant and called as capacitance, capacity of that conductor, or it is also called as capacitance. So we can write the formula of C. C is equal to Q by V. So we get formula for capacity Q by V, or you can use capital Q. Capital Q, small q, it doesn't matter. Only here you remember capacity is charged by potential. If I consider V is 1 volt, then C is equal to Q. Means capacity is charge per unit volt or charge per unit potential difference. Or you can write capacitance of conductor is defined as charge required to raise potential by 1 volt, by unit volt. Okay. Capacitance, by using this capacitance or capacitance of conductor is defined as charge required to raise potential through 1 volt or 1 unit. SI unit of capacitance is farad. So farad is the name of scientist. So generally we use it in term of capital F. Symbol is, this is the symbol of capacitance. Or you can write like this way also. You know the formula, this is the formula of capacity. Unit is farad. Or you can write 1 farad is equal to 1 coulomb divided by 1 volt. Now dimension of capacitance is L minus 2, M minus 1, T raised to 4, A raised to 2. By substituting dimension of charge and dimension of potential, we get the dimension of capacitance. Capacitance is said to be 1 farad. You can see here this formula. When 1 coulomb, you can see 1 coulomb of charge raises the potential by 1 volt. This formula we have written this. Farad is a very large unit. Generally, if you see this farad, it is a large unit. Generally, we are not, you can see a unit of the capacity in a problem. Generally, it is in micro, nano, picofarad. Because farad is a very larger unit. So we use capacity in terms of millifarad, microfarad, nanofarad, or picofarad. So here micro means what? 10 raised to minus 6 farad. Nano means 10 raised to minus 9. Pico means 10 raised to minus 12 farad. So these prefixes you have to use to solve the problems. Generally in a problem you can see capacity in micro, nano, picofarad. Principle of capacitance or principle of capacitor. Now consider a plate A. We consider plate A is positively charged. So plate A having positive charge. And one more plate we consider B, which is neutral. No charge on that. ठीक है. If we consider two plate A which is positively charged, plate B which is neutral, V is potential difference. V is potential difference across plate A. Q is the charge on plate A. Then, so you can see the plate A and plate B. Plate A positively charged. You can see here plate A which is a positively charged, and plate B is a neutral, no charge on the plate B. We consider V is potential across A, Q is the charge on A. ठीक है. Then capacity. Then capacity is given by this formula. So this is the capacity of plate A. C is equal to Q by V. We use C1. ठीक है. Step 2, you can see when this neutral plate B is brought near A. When this plate B is brought or is moved towards plate A, charges are induced. Now basically this plate B is uncharged, but when as we move this plate B towards the plate A, charges are induced. Okay? Charges are induced on B such that side near A is negative and other side is positive. Means on this side negative charge and on this side positive charges are induced. You can see now in a diagram. So let me show these charges, induced charges in a diagram. Before that, one more point we consider. When the further side of B is earthen, when the plate B is earthen means it is grounded, it is connected to ground. Positive charges on B gets neutralized and B is left with negative charges. Pay attention. So here negative charges are produced and to this side positive charges are produced as per step 2. Okay. After that, as per step 3, if we earthen it, earthen means if we ground it, you can see here. If we connect this plate B outside portion to ground, then these positive charges escape to ground. It means that the plate B live with only negative charges. You can see here. Plate B live with only negative charges. Now the net potential of system decreases. Then potential of the system decreases. Here the potential due to the positive charges and here it is potential due to negative charges. Then potential decreases. Okay, potential decreases due to sum of positive potential on A and the negative potential on B. On B negative potential develop, on A positive potential. Total potential is addition of that. So the net potential decreases. Now, whatever we covered in step 2, step 3, that we recall again. So this is positively charged plate A, B is uncharged plate. Now we have to bring this plate B towards plate A. You can see. Then negative charges on inner portion of B and positive charges on outer portion. You can see here. Negative and other side is positive. Now B is earthen. Means we have to connect B to the ground. You can see here. So here we connected this B to the ground. Then these positive charges, you can see here, positive charges escape to ground. No positive charge on the plate B. So this is the plate B. Only the plate B live with negative charges. Okay. Now I consider here minus V1 is the potential due to this plate. So minus V1 is potential due to this negative charges. And here the potential is what we can see. So here the resultant potential is V plus minus V, means addition of these two. So this potential plus this potential is the total potential. So you can see here. So total potential is V minus V1, net potential of the system. Therefore, the capacity is, so we can write capacity of this combination is Q upon a net potential, and net potential is V minus V1. V minus V1 is the net potential. So this is the capacity of this combination. For this combination, capacity is given by this form. But here, if you see this, in this formula, equation 1 and this equation 2. So in equation 1, V is there. Here V, and it's a V minus V1. So if we compare these two potential, then V is greater than V minus V1. As V is greater than V minus V1. It means that from 1 and 2, this C1 is less than C2. So as because of this, you can see here, this V is greater. If this V is greater, then C1 is less. So we get C1 less than C2. Means we have capacity increase. So here the capacity is C1, and for this combination capacity is C2. It means that when we do this type of combination, when we arrange this type of conductor combination, the capacity increases. And it is nothing but the capacitor. Means capacitance, capacitor, condenser is basically arrangement of the conductor in such a way that the capacity increases. Means it stores large charge, but the potential must be less. You can see here the potential must be less, and that arrangement of the conductor is called as capacitance. I hope you understood this capacitor article, principle of the capacitor. Basically, capacitors are classified into three types. First one is, before this series combination, you can remember the types. First one is parallel plate capacitor. Parallel plate capacitor. In that parallel plate capacitor, so two plates are there, the plate A and plate B. Plate A is positively charged plate. Then when plate B is uncharged, when we bring closer to this, closer to A, then negative charges are produced on inner portion of B and positive charges are grounded. This is a parallel plate capacitor. Second one is spherical plate capacitor. Spherical capacitor. In spherical capacitor, two concentric spheres are there. Inner sphere, to the inner sphere we are given positive charge, and outer sphere is uncharged. Then negative charges are induced on inner portion and positive on outer portion. When we ground it, positive charges escape to the ground. And the third one is cylindrical capacitor. Cylindrical capacitor. So it consists of two coaxial cylinders. A charge is given, positive charge is given to the inner cylinder, and this is the outer cylinder. Then negative charges induced on inner portion of this cylinder, outer cylinder, and the positive charges on outer portion. These positive charges are grounded. Okay, these are the three types of the capacitor. I hope you understood this. Series combination of capacitors. We consider a capacitor C1, C2, C3. They are connected in series. Series means one after another. So this is series combination. And the combination is connected across a battery of potential V. Now in series, charge is same in each capacitor. So battery sends some charge Q. So this charge is same on all the three capacitor. The potential is distributed in inverse proportion to capacitor. Now we can consider here. So this charge here we consider small q. Take a small q. Small q is charge on C1, C2, and C3. Potential on C1 is V1. On V2, V2 is the potential on capacitor C2. V3 is the potential on C3. Total potential is V. So we can write by using this diagram V is equal to V1 plus V2 plus V3. If we add V1, V2 and V3, we get V. So we write the equation. V is equal to V1 plus V2 plus V3. But we know the formula of capacity. C is equal to Q by V. Sorry, we can use small q, capital Q, doesn't matter. Q by V. By using that, we get a formula of V, Q by C. So V1 formula we can write. V1 is equal to Q by C1. So why not Q1? Because you can see in a diagram. So same charge Q is passed through all the capacitors. So we cannot write Q1, Q2. So Q is same. So V1 is Q by C1. V2 is Q by C2. Similarly, we can write V3 is equal to Q by C3. You can see these values. Now these values we have to substitute in above equation of V. So we get here after substitution. So V is Q by C, V1 is Q by C1, V2 is Q by C2, V3 is Q by C3. We substitute these values. Then here we can take Q common. So we can take Q common here. So Q get cancelled. Okay, as we cancel the Q, we get 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. And this is expression for capacity in series combination. Now here this is the general formula. When the three capacitors are used, this is the formula. If it is 4, then plus 1 by C4 we can add at the end. So in general, we can write. So this is the formula in general. 1 by C is equal to summation of summation 1 upon Ci, and the I is varying from 1 to n. Okay, this is the formula of capacity in series combination. So if n number of capacitors having equal capacity C connected in series combination. So instead of 3, we consider n number of capacitors. They are connected in series. Then the formula for this capacity in series is equal to C by n. Capacity of one capacitor divided by the number of capacitors. So this is a formula for resultant capacity. Capacitors in parallel combination. Again, we consider the capacitor, three capacitors, C1, C2, C3. They are connected in parallel combination across a battery of potential V. You can see it in diagram. Now in parallel combination, potential is same. This V is same. V is not changing. V is same for all the three capacitors. Charge is distributed in direct proportion to capacitor. Okay. Now we consider this capacitor, this battery send a charge Q. Now charge through this C1 is Q1. Charge through this C2 capacitor is Q2. And this C3 is Q3. In the same charge, now here charge is not same. We say battery send the charge Q and it is divided into three parts, Q1, Q2, Q3. So we can write Q is equal to addition of Q1, Q2 and Q3. So we can write this formula. Q is equal to Q1 plus Q2 plus Q3. Now by using this formula of capacity, C is equal to Q by V. So by using that, Q is equal to CV. By using that, Q is equal to CV. So Q1 is equal to C1V. We are not writing V1 because V is same for all. Q2 is equal to C2V. Q3 is equal to C3V. And Q we can write CV by this formula. Now we substitute these in the above equation. We get CV is equal to C1V plus C2V plus C3V. Now from this right hand side we can take V common. Then we get cancelled from both the side. Then we get the formula C is equal to C1 plus C2 plus C3. This is the formula. In general, we can write summation of Ci. If 4 capacitor, then at the end plus C4 we can write. If means here we can say that effective capacitance is sum of individual capacitors here. Now pay attention, if n number of capacitors having equal capacity C, they are connected in parallel combination. The capacity is n into C. The capacity is given by formula n into C. Simple example we can take. So if I consider this is 10 microfarad, this is 10 microfarad, this is 10 microfarad, then total capacity is C is equal to 10 plus 10 plus 10 is 30. Or by using the same formula, the 3 capacitor multiplied by each having capacity 10, so it is coming 30. Now what is dielectrics? Generally, a non-conducting medium or insulator is called as dielectric. Precisely, non-conducting material in which induced charges are produced on their faces on the application of electric field are called as dielectric. Example: air, H2, glass, mica, paraffin, wax, etc. These are the example of dielectric. Polarization of dielectric. Now what is polarization of dielectric? So when non-polar dielectrics act, so you note this word, when non-polar dielectric slab is subjected to electric field, dipole are induced due to separation of positive and negative centers. So this is a positively charged plate, this is negatively charged plate. In between this dielectric material is there, and it is a non-polar dielectric. Here we highlighted this word, non-polar. And when we apply the electric field E0 to this dielectric slab, then so here some dipole are induced, and because of that some electric field is created, and it is EP. EP is the electric field due to this dielectric. So E0, you can see here, E0 is the applied field. EP is the induced field. Induced field due to this dipole. So resultant electric field is, so you can see here, resultant electric field is E0 minus EP, because resultant electric field is vector addition of these two, and these two having opposite direction. So E0 minus EP is the resultant electric field. Dielectric constant. By using this, we can find out dielectric constant given for this dielectric slab is given by this formula. E0 divided by E0 minus EP. This is the formula for dielectric constant that you remember. Dielectric constant E0 upon E0 minus EP. E0 is applied electric field, and E0 minus EP is the resultant electric field or net electric field. So this is the formula for the dielectric. After this, polarization vector. What is polarization vector? Polarization basically measures the degree of polarization of dielectric. It measures the degree of polarization of dielectric, and it is defined as dipole moment of unit volume of polarized dielectric, or dipole moment per unit volume. Electric dipole moment per unit volume is the polarization. Or we can write this polarization in terms of susceptibility. So here you can see P for polarization. Xe is electric susceptibility. E is electric field intensity. So where X is the constant, and this constant is called as electric susceptibility. Electric susceptibility is the constant for that electric medium that you remember. And in this formula E is the electric intensity. Now dielectric constant of various material we discuss, the values we consider here. You can see here dielectric constant for a certain material when we are talking about this air. So for air, dielectric constant is minimum and maximum, you can see. Okay, it is for air, dielectric constant is 1. For other medium, dielectric constant having a different value, but these values is greater than 1. And for metal, you can see here dielectric constant is, for metal it is infinity. Means here you remember dielectric constant K is equal to 1 for air, but other medium, for other medium dielectric constant is always greater than 1. For other medium it is 1. Okay? And for air it is 1. For air or vacuum it is 1, and other medium it is greater than 1. And for metal it is infinity. Now new article we have to start, and it is capacitors. So what is capacitors? Capacitor is a device generally used for storing electric charge. Capacitor is a device for storing electric charge. The measure of ability of conductor to store charge in is known as capacitance or capacity. The ability of conductor to store charges is known as capacitance or capacity. Ability, every conductor having its own ability to store charges, and it is capacitance or capacity. Now you know that when we are considering about an uncharged conductor, as we start increasing charges on the conductor, then its potential also start increasing. So as charge increases, potential increases. So we can write Q proportional to V. As charge increases, potential increases. Hence we can write the same equation by writing constant. So Q is equal to CV, and where C is a constant and called as capacitance, capacity of that conductor, or it is also called as capacitance. So we can write the formula of C. C is equal to Q by V. So we get formula for capacity Q by V, or you can use capital Q. Capital Q, small q, it doesn't matter. Only here you remember capacity is charged by potential. If I consider V is 1 volt, then C is equal to Q. Means capacity is charge per unit volt or charge per unit potential difference. Or you can write capacitance of conductor is defined as charge required to raise potential by 1 volt, by unit volt. Okay. Capacitance, by using this capacitance or capacitance of conductor is defined as charge required to raise potential through 1 volt or 1 unit. SI unit of capacitance is farad. So farad is the name of scientist, so generally we use it in term of capital F. Symbol is, this is the symbol of capacitance, or you can write like this way also. You know the formula, this is the formula of capacity. Unit is farad. Or you can write 1 farad is equal to 1 coulomb divided by 1 volt. Now dimension of capacitance is L minus 2, M minus 1, T raised to 4, A raised to 2. By substituting dimension of charge and dimension of potential, we get the dimension of capacitance. Capacitance is said to be 1 farad. You can see here this formula. When 1 coulomb, you can see 1 coulomb of charge raises the potential by 1 volt. This formula we have written this. Farad is a very large unit. Generally, if you see this farad, it is a large unit. Generally, we are not, you can see a unit of the capacity in a problem. Generally, it is in micro, nano, picofarad. Because farad is a very larger unit. So we use capacity in terms of millifarad, microfarad, nanofarad, or picofarad. So here micro means what? 10 raised to minus 6 farad. Nano means 10 raised to minus 9. Pico means 10 raised to minus 12 farad. So these prefixes you have to use to solve the problems. Generally in a problem you can see capacity in micro, nano, picofarad. Principle of capacitance or principle of capacitor. Now consider a plate A. We consider plate A is positively charged. So plate A having positive charge. And one more plate we consider B, which is neutral. No charge on that. Okay? If we consider two plate A which is positively charged, plate B which is neutral, V is potential difference. V is potential difference across plate A. Q is the charge on plate A. Then, so you can see the plate A and plate B. Plate A positively charged. You can see here plate A which is a positively charged. And plate B is a neutral, no charge on the plate B. We consider V is potential across A, Q is the charge on A. Okay? Then capacity. Then capacity is given by this formula. So this is the capacity of plate A. C is equal to Q by V. We use C1. Okay? Step 2 you can see when this neutral plate B is brought near A. When this plate B is brought or is moved towards plate A, charges are induced. Now basically this plate B is uncharged. But when as we move this plate B towards the plate A, charges are induced. Okay? Charges are induced on B such that side near A is negative and other side is positive. Means on this side negative charge and on this side positive charges are induced. You can see now in a diagram. So let me show these charges, induced charges in a diagram. Before that, one more point we consider. When the further side of B is earthen, when the plate B is earthen means it is grounded, it is connected to ground. Positive charges on B gets neutralized and B is left with negative charges. Pay attention. So here negative charges are produced and to this side positive charges are produced as per step 2. Okay? After that, as per step 3, if we earthen it, earthen means if we ground it, you can see here. If we connect this plate B outside portion to ground, then these positive charges escape to ground. It means that the plate B live with only negative charges. You can see here. Plate B live with only negative charges. Now the net potential of system decreases. Then potential of the system decreases. Here the potential due to the positive charges and here it is potential due to negative charges. Then potential decreases. Potential decreases due to sum of positive potential on A and the negative potential on B. On B negative potential develop, on A positive potential. Total potential is addition of that. So the net potential decreases. Now, whatever we covered in step 2, step 3 that we recall again. So this is a positively charged plate A. B is uncharged plate. Now we have to bring this plate B towards plate A. You can see. Then negative charges on inner portion of B and positive charges on outer portion. You can see here. Negative and other side is positive. Now B is earthen. Means we have to connect B to the ground. You can see here. So here we connected this B to the ground. Then these positive charges, you can see here, positive charges escape to ground. No positive charge on the plate B. So this is the plate B. Only the plate B live with negative charges. Okay. Now I consider here minus V1 is the potential due to this plate. So minus V1 is potential due to this negative charges. And here the potential is what? V. You can see. So here the resultant potential is V plus minus V. Means addition of these two. So this potential plus this potential is the total potential. So you can see here. So total potential is V minus V1, net potential of the system. Therefore, the capacity is, so we can write capacity of this combination is Q upon a net potential, and net potential is V minus V1. V minus V1 is the net potential. So this is the capacity of this combination. For this combination, capacity is given by this form. But here, if you see this, in this formula, equation 1 and this equation 2. So in equation 1, V is there. Here V, and it's a V minus V1. So if we compare these two potential, then V is greater than V minus V1. As V is greater than V minus V1. It means that from 1 and 2, this C1 is less than C2. So as because of this, you can see here, this V is greater. If this V is greater, then C1 is less. So we get C1 less than C2. Means we have capacity increase. So here the capacity is C1, and for this combination capacity is C2. It means that when we do this type of combination, when we arrange this type of conductor combination, the capacity increases. And it is nothing but the capacitor. Means capacitance, capacitor, condenser is basically arrangement of the conductor in such a way that the capacity increases. Means it stores large charge, but the potential must be less. You can see here the potential must be less, and that arrangement of the conductor is called as capacitance. I hope you understood this capacitor article, principle of the capacitor. Basically, capacitors are classified into three types. First one is, before this series combination, you can remember the types. First one is parallel plate capacitor. Parallel plate capacitor. In that parallel plate capacitor, so two plates are there, the plate A and plate B. Plate A is positively charged plate. Then when plate B is uncharged, when we bring closer to this, closer to A, then negative charges are produced on inner portion of B and positive charges are grounded. This is a parallel plate capacitor. Second one is spherical plate capacitor. Spherical capacitor. In spherical capacitor, two concentric spheres are there. Inner sphere, to the inner sphere we are given positive charge and outer sphere is uncharged. Then negative charges are induced on inner portion and positive on outer portion. When we ground it, positive charges escape to the ground. And the third one is cylindrical capacitor. Cylindrical capacitor. So it consists of two coaxial cylinders. A charge is given, positive charge is given to the inner cylinder, and this is the outer cylinder. Then negative charge is induced on inner portion of this cylinder, outer cylinder, and the positive charge is on outer portion. These positive charges are grounded. Okay, these are the three types of the capacitor. I hope you understood this. Series combination of capacitors. We consider a capacitor C1, C2, C3. They are connected in series. Series means one after another. So this is series combination. And the combination is connected across a battery of potential V. Now in series, charge is same in each capacitor. So battery sends some charge Q. So this charge is same on all the three capacitor. The potential is distributed in inverse proportion to capacitor. Now we can consider here. So this charge here we consider small q. Take a small q. Small q is charge on C1, C2, and C3. Potential on C1 is V1. On V2, V2 is the potential on capacitor C2. V3 is the potential on C3. Total potential is V. So we can write by using this diagram V is equal to V1 plus V2 plus V3. If we add V1, V2 and V3, we get V. So we write the equation. V is equal to V1 plus V2 plus V3. But we know the formula of capacity. C is equal to Q by V. Sorry, we can use small q, capital Q, doesn't matter. Q by V. By using that, we get a formula of V, Q by C. So V1 formula we can write. V1 is equal to Q by C1. So why not Q1? Because you can see in a diagram. So same charge Q is passed through all the capacitors. So we cannot write Q1, Q2. So Q is same. So V1 is Q by C1. V2 is Q by C2. Similarly, we can write V3 is equal to Q by C3. You can see these values. Now these values we have to substitute in above equation of V. So we get here after substitution. So V is Q by C, V1 is Q by C1, V2 is Q by C2, V3 is Q by C3. We substitute these values. Then here we can take Q common. So we can take Q common here. So Q get cancelled. Okay, as we cancel the Q, we get 1 by C is equal to 1 by C1 plus 1 by C2 plus 1 by C3. And this is expression for capacity in series combination. Now here this is the general formula. When the three capacitors are used, this is the formula. If it is 4, then plus 1 by C4 we can add at the end. So in general, we can write. So this is the formula in general. 1 by C is equal to summation 1 upon Ci, and the I is varying from 1 to n. Okay? This is the formula of capacity in series combination. So if n number of capacitors having equal capacity C connected in series combination. So instead of 3, we consider n number of capacitors. They are connected in series. Then the formula for this capacity in series is equal to C by n. Capacity of one capacitor divided by the number of capacitors. So this is a formula for resultant capacity. Capacitors in parallel combination. Again, we consider the capacitor, 3 capacitors, C1, C2, C3. They are connected in parallel combination across a battery of potential V. You can see it in diagram. Now in parallel combination, potential is same. This V is same. V is not changing. V is same for all the 3 capacitors. Charge is distributed in direct proportion to capacitor. Okay. Now we consider this capacitor, this battery send a charge Q. Now charge through this C1 is Q1. Charge through this C2 capacitor is Q2. And this C3 is Q3. In the same charge, now here charge is not same. We say battery send the charge Q and it is divided into 3 parts, Q1, Q2, Q3. So we can write Q is equal to addition of Q1, Q2 and Q3. So we can write this formula. Q is equal to Q1 plus Q2 plus Q3. Now by using this formula of capacity, C is equal to Q by V. So by using that, Q is equal to CV. By using that, Q is equal to CV. So Q1 is equal to C1V. We are not writing V1 because V is same for all. Q2 is equal to C2V. Q3 is equal to C3V. And Q we can write CV by this formula. Now we substitute these in the above equation. We get CV is equal to C1V plus C2V plus C3V. Now from this right hand side we can take V common. Then we get cancelled from both the side. Then we get the formula C is equal to C1 plus C2 plus C3. This is the formula. In general, we can write summation of Ci. If 4 capacitor, then at the end plus C4 we can write. If means here we can say that effective capacitance is sum of individual capacitors here. Now pay attention, if n number of capacitors having equal capacity C, they are connected in parallel combination. The capacity is n into C. The capacity is given by formula n into C. Simple example we can take. So if I consider this is 10 microfarad, this is 10 microfarad, this is 10 microfarad, then total capacity is C is equal to 10 plus 10 plus 10 is 30. Or by using the same formula, the 3 capacitor multiplied by each having capacity 10, so it is coming 30. Now we have to learn special cases of this formula. Some special cases. Case number 1. If dielectric fills up entire space, then now initially we consider So this is a plate 1, this is plate 2. And between the plate, so the thickness of the dielectric slab is T. So this T is the thickness. So total distance we consider between the two plate is D. So if the entire space is filled with dielectric, now here we consider only that much thickness of the dielectric, then we get this formula. But if we consider entire space is filled with dielectric, then we can write this T is equal to D. The thickness of dielectric slab is equal to this D. So if we substitute T and D is same, if we substitute T and D both are same, then here from the formula this get cancelled. So we get T by K here. And this K is shifted up. So we get formula for capacity. A epsilon 0 K by D. So this is the formula. So this is the formula for the capacity if the entire space is filled with dielectric. Now, in the previous article, without dielectric slab, we get capacity C is equal to, so in that we get C is equal to A epsilon 0 by D without dielectric, and with dielectric A epsilon 0 K by D. So here simply we can write, so capacity with dielectric is equal to K times capacity without dielectric. So we get relation here. Means pay attention. Without dielectric means what? In between the two plates, air is the medium. When that air is replaced by a medium whose dielectric constant is K, then capacity increases K times. A simple example. So here I consider capacitor. I consider capacitor whose capacity with air as a dielectric medium, means no medium between the two plates. So capacity is 10 microfarad. So if this air is replaced by a medium of dielectric constant 3, then capacity with dielectric is K times capacity with air, means 3 multiplied by 10, it is 30 microfarad. So remember this for MCQ purpose. Means capacity increases K times. Or you can write a formula of dielectric constant. Dielectric constant is given by formula capacity with dielectric divided by capacity without dielectric. So this formula gives dielectric constant. Now second case we consider, if capacitor is filled with n dielectric slabs. So n dielectric slabs of thickness T1, T2, T3 Tn. These are the thickness of dielectric slabs. How many dielectric slabs? N. Having dielectric constant K1, K2 Kn. This arrangement is shown in a diagram. You can see this diagram. And this arrangement is equivalent to capacitor connected in series. So when capacitors are connected in series, then you know that capacity is what? Then we can write the total capacity is given by this formula. Total capacity is given by this formula. A epsilon 0 divided by T1 by K1 plus T2. Here T1 is the thickness of this dielectric slab. T2 is the thickness of this dielectric slab. Tn is the thickness of this dielectric slab. So this is the capacity when n number of dielectric slabs having different thickness are introduced. So remember this formula. Now case 3. If arrangement consists of n capacitors in parallel, Now here, this is similar to the series combination. Now we are considering n capacitors in parallel with the plate area A1, A2, dot, 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 AN. And the separation is D. Then capacity, you remember, given by this formula. So here area are different, huh? A1, A2. So epsilon 0 D. Epsilon 0 divided by D in a bracket. A1 into K1 plus A2 into K2 plus dot 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 AN into KN. But if we consider here A1 is equal to A2 is equal to A3 is equal to dot 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 AN. Or we can say that it is A divided by N. Then, so instead of this A1, we can substitute A divided by N. Then we can write equation, this equation as a and this divided by N, we are taken outside. So we get formula of capacity. A epsilon 0 divided by D into N in a bracket K1 plus K2 plus K3 plus dot 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 Kn. So this is the formula of capacity. Now case 3. Sorry, case 4. If capacitor is filled with a conducting slab between the two plates, if we use conducting slab. For conducting slab, K is infinity. Now I consider two plates. This is first plate, this is second plate. Between the two plates, we consider a conducting slab. Between the two plates, we consider the conducting slab. So this is plate P1, this is P2. Then capacity is given by this formula. So here the thickness is T is the thickness and total distance between the plate is D. So that time, so this is the capacity. You remember this formula. C is equal to D upon D minus T into C0. So here C is greater than C0. So capacity is increased by factor here. So capacity you can see here. So same formula we can write like this. C is equal to this D upon D minus T into C0. Means capacity is increased by that factor. D upon D minus T. Dear student, in today's lecture, we have to cover article displacement current. Now, first thing, what is displacement current? Current, everybody know that. Current means rate of flow of charge in the current. Now, what is displacement current? So for that, let I tell you one simple example. When we consider this is a DC source and this is a capacitor. So this is a capacitor whose capacity is C. And when current is sent through this when we close the key, it sends the current. And that current is the conduction current. But you know that symbol of the capacitor generally we use like this. The two plates we use. So this is the symbol of capacitor. Means between the two plate, no medium is there. Then also you can see here the current is passed. So current pass through this between the two plates without the medium also. If we consider a dielectric material means the insulating material. So this dielectric material means the insulating material. Or we can consider air also in between the two capacitor plate. Now this logic is enough to understand this displacement current. Now we know that electric current in DC circuit constitutes flow of free electron.
But in the region between the plates of capacitor, there are no free electrons. Basically, current means flow of free electron, but between the two plates, there are no electrons available for conduction in the dielectric. Dielectric is insulating material, and you know that in any insulating material, no free electrons. Then also current flows. Okay. As the circuit is closed, now here, when we close the circuit, current, so let me use the symbol IC, flows through the circuit. The conduction current, and it is the conduction current, is found to be same everywhere in the circuit except inside the capacitor. And this current IC, you can see here we represented the current by IC. It is same everywhere except between the two plates. Except between the two plates, or inside the capacitor, in short we can say. Now, as the current pass through the leads of capacitor, so these two are the leads of capacitor. As the current pass through the leads of capacitor, electric field between the plates, increases. Pay attention, electric field between the two plate increases, and this in turn causes polarization of dielectric. We learn the polarization of dielectric. The bound charges displaced. Okay. We already learned this article. When dielectric material is exposed to external electric field, what happened, that everybody know. Now there are current in dielectric due to the movement of bound charges. So why the current in dielectric? Due to movement of bound charges. The current due to bound charges is called as displacement current. The current due to this bound charges is called as displacement current. Pay attention, why the current flows through this dielectric, that is very important. So when we apply the external electric field by using this, then the shifting of these positive charges and negative charges, they are well separated. Some electric field is set up, and due to that, well, these positive charges and negative charges separated means they are the movement of the positive and negative charges are produced, and because of that a current is set up, and that current is called as displacement current, or it is also called as charge separation current. It is called as charge separation current. Now here, inside this dielectric, the positive charges of the dielectric shifted in the direction of electric field. Okay? And negative charges opposite to that. Simply you remember here. So why the displacement current is set up? Because of displacement of bound charges. Now, we know that electric field between the plate is given by formula sigma upon epsilon 0. And if we consider a dielectric material whose constant is K, then electric field is sigma upon epsilon 0 K. Sigma upon epsilon 0 K is the electric intensity. Now you know that, so electric intensity between the two plate is sigma upon 2 epsilon 0 plus sigma upon 2 epsilon 0. It is sigma upon epsilon 0. Okay. So that we learn in the derivation of parallel plate capacitor. So electric field between the plate is sigma upon 2 epsilon 0 plus sigma upon 2 epsilon 0. It is sigma upon epsilon 0. But if the dielectric constant is K, we can write sigma upon epsilon 0 K. Now sigma is, but here sigma is charge by area, charge per unit area. So after substituting this, we get E is equal to Q upon A epsilon 0 K. So this is the electric intensity. This is electric intensity. So by using that, we can write the formula of Q. Q is equal to A multiplied by K multiplied by epsilon 0 multiplied by E. So this is the formula of Q. If you differentiate this, we get the current. Let me differentiate this equation. Differentiating the above equation, we get dq by dt. Differentiating with respect to t, we get ak epsilon 0 dE by dt. We get this formula. Now this dq by dt is the current. So I can write IC is equal to ak epsilon 0 dE by dt. Or we can write the formula of dE by dt. So this is the rate of change of electric field. The rate of change of electric field across the capacitor is directly proportional to the current. Means this rate of change of electric field depends on current. So we can write this equation, dE by dt proportional to the current. dE by dt proportional to current if the area of the plate is constant. Now, you remember this equation. If you see this equation very carefully, so this right hand side of this equation having dimension similar to the dimension of current. Between the two plates, dielectric material is there. And if the current flows through between the two plates, it is because of movement of the bound charges. And that current is the displacement current. So therefore, the displacement current we can write in absence of dielectric between the plate. I am considering no dielectric material between the plate. Means K is 1. Since we are considering air or vacuum, the displacement current is given by this formula. Only in that we have to substitute the value of K is 1. We substitute the value of K 1 in that. So we get displacement current is equal to A epsilon 0 dE by dt. This is expression for displacement current. In general, displacement current in a circuit containing capacitor can be stated that displacement current do not remain confined to space between the plates of capacitor. Means it is not related to the space between the capacitor. Displacement current exists at any point where electric field changes. When time varying electric field exists, you remember one thing, displacement current exists anywhere, any point where the electric field changes with time. Means time varying electric field is there. At that point, displacement current is produced. So remember, this is very important sentence. displacement current exists at any point in a space where time varying electric field exists.
Next article is energy stored in a capacitor. When we charge a capacitor, how much energy it stores? So that we can obtain by a formula, and that formula we have to derive here. So we consider a capacitor of capacitance C charged by DC source whose potential is V as shown in figure. You can see here capacitor. It is charged by a source whose potential is V. Now I consider here Q is the final charge, V is final potential. When it is fully charged means when it is a maximum value of the charge. The final charge is Q, V is the final potential. Then capacity is given by formula Q by V. Capacity is given by formula Q by V. And you remember one thing here, capacity is constant. So during charging means what? When we are started adding charge on this capacitor plate. So during charging at any instant, I consider here, it may be we have to consider small q is the final, small q is the charge, small v is potential. During charging, q is the charge and v is the potential. Let us use small v for this potential. Then capacity is given by formula q dash by v. Let's say q dash is the charge. Q dash is the charge and v is the potential. So we get capacity is q dash by v. And both the capacities are same because capacity is constant. A small amount of work done. Now you have to add, pay attention, we are considering a case during charging. So this is very important. During charging we have to consider. So q dash is the charge and v is the potential. That time this is the capacity. So when we want to add a charge dq on a plate, so pay attention, when we are adding the charge on a plate, so this is a plate, this plate already having a positive charge, one more plate we can consider this plate having negative charge. When we are adding a charge on this plate, then I consider the charge is dq. When we want to add a dq charge on this plate, so this is a positive charge and this is a positive plate. So this positive repulsion is there. Against that repulsive force, we have to do some work to add that charge. And that work done we have to write. So pay attention here. Small amount of work is done if a charge dq is further transferred between the plate. When we add this charge dq on the plates, some work is done. And that work done is given by formula V into dq. So this work done is given by formula V into dq. So we know the formula of potential dw by q. By using that, work done is equal to V into q or V into dq. So we get the work done. So but V, by using this formula, so V is equal to q dash by c. So this formula we substitute here. So we get work done is equal to q dash by c. Q dash by c into dq. So this is the work done to add a small charge dq. We have to find out work done, total work done to add a charge q. So because the final charge is q, so we have to find out work done to add a charge from 0 to capital Q. So total work done in transferring the charge is given by formula integration of dW. But integration of dW within a limit 0 to capital Q. Now let me substitute the formula of dW here. Okay. So we get integration 0 to Q, Q dash by C into dQ. Now we take a constant outside. C is a constant that we take outside. So 1 by C is outside. So integration of Q dash into dQ within a limit 0 to Q. Now integration of x dx is coming x square by 2. So Q dQ is Q square by 2. So it's a Q dash. So Q dash square by 2. Now we have to substitute the limit. So initially, instead of Q dash, we have to substitute upper limit, then minus sign, and then lower limit. So we can write like this: 1 by C, Q square by 2 minus 0 square by 2, 0. So we get formula 1 by 2 Q square by C. So this is the formula of work done. This work done is stored in the form of potential energy. This work done is stored in the form of potential energy. That potential energy we can write by symbol U. Hence we can write potential energy is equal to, or you can write electrostatic potential energy stored in capacitor is equal to 1 by 2 Q square by C. So this is expression for energy stored or electrostatic potential energy stored by capacitor. Q square by C, 1 by 2 Q square by C. This energy can be expressed in different forms as follow. We know the formula C is equal to Q by V. So by using this formula, C is equal to Q by V, we can write this energy stored is equal to 1 by 2 CV square. Now how we write? U is equal to 1 by 2 as it is. By this formula, Q is equal to CV. So we can write instead of Q, CV. So we get C square V square by C. So this C and this C get cancelled. We get 1 by 2 CV square is the energy stored. So here we substitute Q is equal to. So instead of Q we substitute, so we get this form. Instead of C also we can substitute Q by V. Instead of C we substitute this formula. Then what we get? So we get formula 1 by 2 QV. So you can see here we get 1 by 2 Q square divided by C is Q by V. So we get 1 by 2, this Q and 1 Q get cancelled. 1 by 2 QV is the formula. So this is expression for energy stored. You can remember different forms for the problem. This is the first equation, second equation, third equation. All the three equations are equivalent. Any one you can remember for the problem, and then as per the given you can substitute this in that formula to obtain the different forms. Now next article is Van de Graaff generator. Now what is Van de Graaff generator? So a diagram you can see. So this device is the Van de Graaff generator. Now what it can do? So it is used to produce high potential. It is used to produce high potential. How much high? Up to 10 raised to 7 volt. And why we are producing high potential? And that high potential used to accelerate charge particle. So that high potential is used to accelerate charge particles. So Van de Graaff generator means what? Device which is used to produce high potential, about 10 raised to 7 volt, and which is used to accelerate charge particle. Now, let's see the principle, then construction and working. Means in detail we learn what is Van de Graaff generator, on what principle it is based, how it works, what are the uses of this Van de Graaff generator. These articles we have to cover. Principle. So it is based on the principle that a hollow conductor in contact to an inner conductor continues to accept charge from the inner conductor. Means in simple word, so when a hollow conductor is coming in contact with another conductor, it start accepting charge. Hollow conductor in contact to inner conductor continues to accept charge from the inner conductor. Second point, if the charge is continuously added to the conductor, potential goes on increasing. Means here, charge increases, potential increases. So this is the main principle. Means here, pay attention. Van de Graaff generator used to produce high potential. So to produce high potential, means if you want to increase V, we have to increase Q, because the principle is Q proportional to V. So this is the principle. To increase V, we have to increase Q. Now how we increase the charge? Let's see. So construction. Construction means whatever we can see in a diagram, that we have to write in word. Now you can see here B dash conveyor belt. So you can see here B dash. So let I highlight it by red color. This is a conveyor belt. So this red color is the conveyor belt, B dash. Now second one is pulleys. P1, P2 is P1 and P2, they are the pulleys. This is P1 and this is P2. These are the two pulleys which run the belt. A, spray brush. You can see here A. So this is a brush. This is a spray brush. And this spray brush is, you can see here, connected to DC supply. It is connected to positive of the DC supply. Okay. Then next one is collector brush. One more similar type of the brush is there, but this brush is collector brush because this is used to collect. So it is called as collector brush. Now next one is D, dome shaped hollow conductor. You can see here. So let I use different color, blue color for this dome shaped conductor. So dome shaped conductor. You can see this type of shape in temple. Inside the temple, you can see the roof of the temple is like dome shaped. So this is a dome shaped conductor, hollow conductor. E, evacuated accelerating tube. Now this is evacuated accelerating tube. Let I use green color here. So this tube, you can, I will shaded the tube. So this tube is evacuated accelerating tube, which is used to accelerate charge particle. I, ion source. I is the ion source.
So here you can see I. It's an electrode or ion source. DC power supply you can see here. So this is a DC power supply. You can see here, this is the power supply. Next one is steel vessel filled with nitrogen. So this is a steel vessel. So this outer surface, full. This is steel vessel which is filled with nitrogen. M, earthen metal plate. Okay, here M you can see. It is a metal plate. So I already explained everything from the diagram. Now we have to see so how everything work. So let's see the construction. Again this diagram, construction. Van de Graaff generator consists of, it consists of conveyor belt BB dash, and this conveyor belt made up of insulating material run by pulleys P1 and P2. You can see here this P1 and P2 used to run this belt by electric motor which is connected to lower pulley. To this lower pulley P1, electric motor is connected, and this electric motor run the belt BB dash. Now a spray brush, A is spray brush, consisting of large number of pointed teeth. It is fixed near lower end of the conveyor belt. You can see here this is fixed at lower end of the conveyor belt, and this is connected to positive terminal of high volt DC source. You can see here the positive terminal. It is connected to positive terminal. Another similar brush C, it is called as collecting brush, connected to large hollow dome shaped conductor D, which is mounted on the insulating stand. So this dome shaped conductor is mounted on the insulating stand, which is not shown in diagram. Now E is, you can see here E. E is evacuated discharge tube which has an accelerating electrode I. So you can see this accelerating electrode I. And this electrode connected to dome shaped conductor. This I is connected to dome shaped conductor. It is connected to dome shaped conductor. And to prevent leakage of charge, to the surrounding, whole arrangement is enclosed in a steel vessel filled with compressed nitrogen. So everything is filled in a steel vessel filled with compressed nitrogen. Why we enclose it? Because charge may leak in a surrounding. To avoid the leakage of charge, it is enclosed. Now working. Now let I explain working. When electric motor connected to pulley P1 switched on, then this conveyor belt rotate. The pulley begin to rotate, setting the conveyor belt in motion. As we switch on this motor, the belt start running on the pulleys P1 and P2. Now DC source is also switched on. As we switch on this DC source, then what happened? This Now the high tension DC source is switched on. The positive charges are spread continuously on conveyor belt. Listen, this brush is connected to positive terminal of the DC source. As we switch on this working of Van de Graaff generator, I will explain working. Now you can see the diagram of Van de Graaff generator. Just we learn construction. So you know all the part of this diagram. Now here you remember one thing here. So when electric motor connected to this pulley P1 is switched on, the belt start moving on this pulley P1 and P2 due to this electric motor. Then second thing, we switch on this DC source. We switch on this DC source. Then this spraying brush A starts spraying positive charges on the belt because this A is connected to spraying brush is connected to positive terminal. So it starts spraying positive charges on belt and belt is in motion. So these positive charges carried in upward direction. Now this near this upper pulley P2, one more collecting brush is there. This C, this collecting brush C collect these positive charges and these charges transfer to outer portion of dome shaped conductor. These charges are transferred to outer portion of dome shaped conductor. As charge on this dome shaped conductor increases, the potential also increases. So due to this accumulation of charges on outer portion of this dome shaped conductor, its potential increases. Because the principle of Van de Graaff generator is charge increases, potential also increases. This dome shaped conductor is connected to electrode of discharge tube. You can see here electrode I. And this electrode get a positive potential or positive charge, positive potential because of this dome shaped conductor, which is positively charged. Now, when we introduce a positive charge, when we introduce positive charge in a discharge tube, this positive charge is repelled by this electrode of discharge tube. Positive charge is repelled by the positive electrode. Positive repulsion is there. And because of that repulsion, so here this positive charge get accelerated. So it gets some velocity. The use of Van de Graaff generator is it is used to accelerate charge particle. So I told you how we accelerate. This positively charged particle is get repelled due to this positive electrode. Generally, this Van de Graaff generator is used to accelerate positively charged particle. We cannot accelerate electron by using Van de Graaff generator. This is working of Van de Graaff generator. I hope you understood whatever I explained. Now this working notes are given here. You can go through later on. Now after that, uses of Van de Graaff generator. Uses of Van de Graaff generator. So you can see here, to carry put nuclear disintegration. First use nuclear disintegration of different element. We can use Van de Graaff generator. So how we are using it, we are not going in that much detail, but you remember here, to carry out this nuclear disintegration of different metal, we can use Van de Graaff generator. To produce radioactive isotope, this Van de Graaff generator is used. To study nuclear structure of different substances, we can use Van de Graaff generator. To study different type of nuclear reactions, to study different type of nuclear reaction by bombarding some uh, element on that. So this Van de Graaff generator is used to study different type of nuclear reaction. It is used to produce electron beam used in sterilization of medical product and packet food atoms. It is used to produce electron beam, which is used for sterilization as well as preservation of the food. So these are the uses of Van de Graaff generator. Dear student, in today's lecture we start a problem based on chapter electrostatic. We start with the MCQ. So MCQ number 1 from the exercise of electrostatic. A parallel plate capacitor is charged and then isolated. The effect of increasing plate separation on charge, potential, capacitance respectively are. So we know that capacity of parallel plate capacitor is given by this formula. Now, if D increased, then what happened to charge, potential and capacitance, that we have to discuss. So first point we discuss about charge. You remember here, charge does not depend on this D. So Q is constant. So first option is constant. You can see in option A is constant. In option C, it start with constant. D also start with constant. So हे तो cut होता है. So option B is eliminated. Now second one is potential. Second one, potential, we have to discuss. So we know that C is equal to Q by V. So V is equal to Q by C. So by that we can discuss what happened to the potential. So before that we discuss about capacitance. C is equal to A epsilon 0 K by D. D increases, then C decreases. So answer here, C decreases. C decreases, you can see here, C means third point, decreases, it is in the option A and option D. So here in the option C, it written increases, so this option is eliminated. So either the answer is option A or option D. Now let me check the potential. So here the potential is Q by C. C decreases means potential increases. So V increases. So V increases. And V increases is written in option D. You can see here. So option D is the right answer for this MCQ 1. Now next question is MCQ number 2 from exercise. Now see here, a slab of material of dielectric constant K has same area A as the plate of parallel plate capacitor and thickness 3 by 4 multiplied by D, where D is the separation of plate. The change in capacitance when slab is inserted between the plate is. So when the dielectric slab is between the
plates of capacitor, then capacity is given by formula A epsilon 0 divided by D minus T plus T by K. So this is the formula. Now in that formula, let me find out this D minus T plus T by K, and then we substitute. So D as it is minus thickness, it is 3 by 4 D plus thickness is 3 by 4 D by K. Now here we can take D common. So it is 1 minus 3 by 4 plus 3 by 4K. Now in that D, so it is coming 4 minus 3 means 1 by 4 plus 3 by 4K. So D, let me do the cross multiplication. 4K plus 12 divided by 16K. Now here we can take 4 common from numerator and denominator, D. So 4 by 4 into this K plus 3 divided by 4K. So these get cancelled. So we get formula here. D in a bracket K plus 3 divided by 4K. So let me substitute here this value. So we get A epsilon 0 divided by D. So K plus 3 divided by 4K. That 4K we can shift up. So we get A epsilon 0 by D in a bracket 4K divided by K plus 3. And this is the answer. And you can see this is the option D. So option D is the right answer for this question. Now next MCQ, and it is MCQ number 3 from exercise. The energy stored in capacitor and dissipated during charging a capacitor, derivation. Now you remember one thing here. So here, energy stored is given by formula half CV square, as well as energy dissipated in capacitor. It is also given by this formula. So when we are taking the ratio of this, we get this 1:1. Now next MCQ is MCQ number 4. A charge plus Q minus Q are placed at point A and B. You can see here at point A and at point B respectively, which are at a distance 2L apart. You can see distance 2L. This is the midpoint of A and B. Work done in moving a charge Q along the semicircle CRD in the figure below. So we have to find out work done. So we can use the formula of potential. So this work by charge, a potential difference. So work done is equal to V into Q, potential difference into charge. So work done to move a charge along this semicircular path. So work done is equal to potential difference. So we are moving charge between the 2 points C and D. So potential difference at D, potential at D minus potential at C into charge is Q, capital Q charge we are moving. Now we have to find out this potential at point D minus potential at point C.
So here, let me substitute potential at point D. So this is a D point. So when we are finding potential at D, we have to find out potential at D due to this plus Q charge and due to this minus Q charge also. So in that, 1 upon 4 pi epsilon 0 is coming common. So that we are taking out. So potential at point D due to this plus Q charge. So Q by distance. Distance is, this is 2L and that distance is L. So 3L. Okay. Now due to this minus Q charge, it is coming due to this minus Q charge at point D. So it is coming minus Q by distance is L. Again, minus sign. Then potential at C. Potential at C again due to both the charges. Due to plus Q charge, it is Q by L. And due to this minus charge, it is minus Q by, again, distance of the C from the minus Q charge is L. So that we have to solve 1 upon 4 pi epsilon 0 Q by 3L minus Q by L minus Q by L plus Q by L. So these get cancelled. So it is 1 upon 4 pi epsilon 0 into this capital Q. So that capital Q, I will write it here. So here, Q by 3L minus, so let us write here 3Q minus 3L. So here we get Q upon 4 pi epsilon 0 in a bracket. Q minus 3Q, so minus 2Q divided by 3L. So let I write it remaining steps here. So Q upon 4 pi epsilon 0. Okay. This minus 2Q by 3L. So it is coming minus 2Q divided by 12 pi epsilon 0 L. So we get the final answer. So 2 6 are 12. So we get the final answer of the work done minus Q into Q divided by 6 pi epsilon 0 L. So this is the work done. And you can see this work done is written in the option A. So option A is the right option for this question. Now question number 5. It's MCQ number 5 from exercise. A parallel plate capacitor has circular plate of radius 8 centimeter. Means it is 8 into 10 raised to minus 2 meter. Plate separation 1 mm. Means it is 1 into 10 raised to minus 3 meter. What will be the charge on plate if the potential difference 100 volt? We can write 10 raised to 2 volt is applied. So we have to find out here charge. We know that C is equal to Q by V. So Q is equal to CV. So we can write here C is equal to A epsilon 0 D divided by D into V. So here area is not given, but it's circular plate. So area is pi r square epsilon 0 into V divided by D is the formula. In that formula we have to substitute. So pi is 3.14 multiplied by r is 8 into 10 raised to minus 2 square into epsilon 0 8.85 into 10 raised to minus 12 into V is 10 raised to 2 divided by D.
and D is 1 into 10 raised to minus. So this we have to solve. So it is 3.14 into 8 square is 64, 10 raised to minus 2 square is minus 4, multiplied by this 8.85 into 10 raised to minus 12 and 2, it is 10 raised to minus 10, divided by 10 raised to minus 6. Now here 8.85 into 64 into 3.14. So that we have to solve. Maybe so by that answer we can conclude that 1780 is the answer by that. And here 10 raised to minus 14 divided by 10 raised to minus 6, 10 raised to minus 11 it is coming. So after solving this 1.780 into 10 raised to minus 8 Coulomb. So the answer for this question is option A. Now next question is problem number 11 from exercise. A charge 6 microcoulomb is placed at origin. You can see here. At origin you can see here 6 microcoulomb charge. And another charge minus 5 microcoulomb is placed on y axis at A. The coordinates are 0, 6.0. So x coordinate is 0 and y coordinate is 6. It means that this distance is 6 meter. Okay. Calculate the point number A. Calculate the total electric potential at point P. So at point P we have to find out potential, whose coordinates are 8.0, 0. X coordinate is 8. It means that this distance is 8 meter. Okay. Second point, calculate work done to bring a proton from infinity to a point P. So what is significance of negative sign? Now in this problem, what they given here? So we say that this charge as a Q1 minus 5 microcoulomb. So that we converted into coulomb by multiplying 10 raised to minus 6. Second charge is 6 microcoulomb. In coulomb it is 6 into 10 raised to minus. So distance is R1 is AP. And this distance of this point P, distance of the P from this one is, we can use Pythagoras. You know that this is 6, this is 8. By Pythagoras, you can find out it's 6 square plus 8 square is 100. 100 root 100 means 10. This is 10 meter. So it is 10. And this R2 distance means distance of the point from the charge is, it is 8. You can see this is 8. So why we find out this distance? Because we require distance of the point P from both the charges. The charge 1 and charge 2. So these are the distances. Now the potential at point P is the potential due to the charge minus 5 microcoulomb plus potential due to charge 6 microcoulomb. So V is equal to V1 plus V2. So we can write the formula. You know that V is given by formula 1 upon 4 pi epsilon 0 Q by R. So we use this potential formula and we have written the formula of the potential here. So we get this formula. Now we have to substitute the values. You know that here 1 upon 4 pi epsilon 0 is 9 into 10 raised to 9 in SI. So with that we can take that common. And this 10 raised to minus 6 is also common in the value of charge, that is also taken common. Then here we can write the charge value is minus 5. The 10 raised to minus 6 is taken common. Minus 5 by 10 plus 6 by 8. So after solving this calculation, we get the answer 2.25 into 10 raised to 3 volt. This is the potential at point P due to both the charges. Similarly, in point B, we have to find out work done to bring a proton from infinity to point P. So work done in bringing a proton from infinity. So we can write a formula of the work done is equal to the formula of potential energy. Or simply we can use this potential formula. Potential is work by charge. This formula we already used in the previous MCQ. So work done is V into Q. This minus sign indicates that this work is done against the electrostatic force or against the direction of electric intensity and so on. Now here potential is known, just we obtain the potential. And the charge of proton is equal to the charge of electron. So 1.6 into 10 raised to minus 90. And this minus sign as it is. After solving this, we get work done is equal to minus 3.6 into 10 raised to minus 16 joule. And this is the work done to bring a proton from infinity to point P. Negative sign, work is done against the electrostatic force. Now, next question is problem number 10 from exercise. Dipole moment of water molecule is, dipole moment generally represented by P, 6.3 into 10 raised to minus 3 Coulomb meter. A sample of water contains 10 raised to 21 molecules, number of molecules whose dipole moment are oriented in an electric field strength. So this is the electric intensity. Calculate work done to rotate dipole from their initial orientation to one in which all the dipoles are perpendicular. Now here, let's see the solution here given. So dipole moment, electric intensity is given and the number of molecules. Now work done is given by formula PE cos theta 1 minus cos theta 2. Let me substitute the values. Theta 1 is here 0 and theta 2 is here 90. So after, you know that cos 90 is 0. So this term get cancelled. We get PE cos theta. Okay. So it is P. This is E. And cos theta means cos 0 is 1. So this is the values. Then after doing the multiplication, we get the answer. So work done is equal to 1.575 into 10 raised to minus 24. And this is work done to rotate dipole. Now pay attention here. This is the work done to rotate dipole for single molecule. But how many molecules are there? 10 raised to 21. So total work done we find out. So it is 10 raised to 21 multiplied by this work done for the single molecule. So let me solve this one. 10 raised to 21 multiplied by this. So after solving this, we get a work done. And it is 1.575 into 10 raised to minus 3. This is total work done to rotate dipole. Now next question. It's problem number 12 from exercise. A parallel plate capacitor with air between the plate. Each plate has area 6 into 10 raised to minus 3 meters square, and the separation between the plate is 2 mm. And this is D, or in meter 2 into 10 raised to minus 3 meter. Calculate capacitance of capacitor. Take it one by one. Let's see the first given here. So given is area, radius, sorry, separation between the plate is there. So we can write D for this. And V. We have to find out capacitance, charge on capacitor. ठीक है. The first point, capacitance. So capacitance is given by this formula. So this is D. So epsilon 0 is 8.85 into 10 raised to minus 12 in SI system, multiplied by area divided by D, D in meter. After solving this, we get capacitance is 2.655 into 10 raised to minus 11 farad. Second point, charge on plates of capacitor. So charge, you know that C is equal to Q by V. So charge is CV. So C we already have, and V is given 100 volt. So we get the calculation. This C multiplied by V. So only the power changes. 2.655 into 10 raised to minus 9 Coulomb is the answer. Third point, change in charge of capacitor. You can see the point C. How would charge on capacitor on the plates be affected if 2 mm thick mica sheet whose dielectric constant is 6 inserted between the plates and the voltage supply remains connected? So we already know that the capacity means change in the charge is equal to K times the original charge when we inserted the dielectric slab. So we get a K is 6 and the Q is here. We substitute Q and that Q multiplied by 6 is the answer. So here we get answer 1.593 into 10 raised to minus 8 Coulomb is the answer for this problem. Now next question is question number 13 from exercise. Find the equivalent capacitance between P and Q. So area is A and separation between the plate is D. So this is first combination and this is the second combination. We have to find out capacitance. Now let's see the solution here. So here are three capacitors. This is, here you can see three tires. This is the first capacitor, this is second and third. They are connected in series. So you know that in series, so the capacity is, resultant capacity is 1 upon C1 plus 1 upon C2 plus 1 upon C3. So that formula we have to use here. So resultant capacity in series is this. And here C1, C2, C3 is how much? So here C1 is A epsilon 0 K1 divided by distance is 3 by 3. You can see here distance between these two plates is D by 3 and the dielectric constant is K. So you know that C is equal to A epsilon 0 K by D is the formula of capacity. So by that formula, so only this K and this D is changing. Okay, by that we have written this. Now let me substitute C1, C2, C3 in the equation, this equation. So we get 1 by C is equal to this D by 3 shifted up. We get this after substitution. We have to solve this to get the answer. Let me take D by 3 common. Then after taking D by 3 common, what we get here? So here 1 by A epsilon 0 plus 1 by 3 epsilon 0 plus 1 upon 6 A epsilon 0. So after adding this, we get 9 upon 6 A epsilon 0 and this D by 3. So this is 1 by C. We have to write C. Okay, we have to write C by using that. So 3 3s are 9. Okay, and 3 2s are 6. So we can write it is D upon 2A epsilon 0. So C is equal to 2A epsilon 0 divided by D. This is the capacity of this first combination. So for this. Now, similar manner for the second combination also we have to find out. Now these two are in the series. In the series, this first, let's say first, this second, and this is third. So this second and third, they are in series, and first and this combination, they are in parallel. Now let me solve in similar way. This second arrangement is equivalent to the first, is equivalent to first capacitor in parallel with the series combination of second and third. This is 1, 2, 3. Now here the series combination we find out for 2 and 3. You know that in series capacities are added. C is equal to C2 plus C3. This is C2, this is C3. You can see here this K is, or you can write like this way also, A epsilon 0. So here area is same. Okay. A epsilon 0 K1 by D1 plus A epsilon 0 K2 by D2. After substituting this, we get this. So area is A by 2 and K here 3 and 6. Now we have to simplify this. So this we can write after simplification 18 A epsilon 0 divided by D by 9. Just wait here. We can take 2 common here. This 2 get cancel. Then 3 A epsilon 0 by D plus 6 A epsilon 0 by D. So it is coming. Just wait. Hello student. So I think here some printing mistake is there. So that's why I erase this problem again. Now see here. So this combination, this is 1, 2, 3. So this 2 and 3. So they are in series. So we find out their capacitance first. So the capacitance in series. So 1 by C S is equal to 1 by, let's say, C2 plus 1 by C3. So is equal to, so 1 upon C2 is, you know that C is equal to epsilon 0 K by D. So how much is the area? So it is area A by 2 epsilon 0, and this K is 3 divided by D is D by 2. So this is C2 plus 1 by C3, area multiplied by epsilon 0 multiplied by K divided by D by 2. Okay. Now we can cancel here. So this this two get cancelled. So we get the next equation is equal to, so this D we can shift up, D upon 3 A epsilon 0 plus D upon 6 A epsilon 0. Now this is 1 upon CS is equal to, now we can write here 2D upon 6A epsilon 0 plus D upon 6A epsilon 0. So we get here 3D upon 6A epsilon 0 It is 1 upon Cs. So it is 3 ones are 3 twos are. So we get here d upon 2a epsilon 0. So Cs is equal to 2a epsilon 0 by d. You note down, this is a series capacitance of this second and third combination. Now here we can write the capacity is equal to the first capacitor. Now you can see here, so this is the first one, and this series combination of 2 and 3, they are in parallel. So I can write the formula here. This C1 plus Cs is the total capacitance. So C1, how we write by this formula? We can write Cs by this formula. Area A by 2, epsilon 0, K is 4, divided by D is, so this is the D, plus 2A epsilon 0 by D. Now here 2 2s are 4. So we get 2A epsilon 0 by D plus 2A epsilon 0 by D. So here we get the answer 4A epsilon 0 by D is the capacity of this combination. So this is the answer. Now you go through this question. This is a little tricky, but this is easy, not that much difficult. Now today we stop here.